Black holes are the strangest objects in the universe. For most of human history, they were nothing more than equations on paper, ideas so extreme that even Einstein himself doubted they could exist. And yet, 55 million light-years away, one of the largest black holes known is hiding inside the giant galaxy Messier 87. In 2019, we looked straight into its abyss. Using a telescope the size of Earth, scientists captured the first ever image of a black hole. It was the moment an invisible monster finally revealed its shadow. This is the story of that black hole, the galaxy it lives in, and the journey of the scientists who brought the invisible into view. The Colossus within Virgo. Far beyond the reach of our own Milky Way lies the giant galaxy Messier 87, or simply M87. It sits quietly in the heart of the Virgo cluster, a crowded region of space where thousands of galaxies gather. To the naked eye from Earth, M87 is invisible, hidden behind the black backdrop of the night sky. But with telescopes, it becomes a ghostly oval glow. What appears faint and hazy to us is, in truth, one of the most massive galaxies we have ever found. A vast kingdom of stars and matter orbiting together in silence across 55 million light-years of distance. Unlike the graceful spirals we are so used to seeing in astronomy books, M87 does not wind itself into elegant arms. Instead, it is an elliptical galaxy, a swollen ball of light that seems to have traded beauty for sheer scale. Spirals like our Milky Way may hold hundreds of billions of stars, but M87 dwarfs them, containing not only hundreds of billions, but possibly even trillions. Every dot of light inside its halo represents a sun, and around those suns circle worlds we will likely never see. It is the kind of galaxy that makes the Milky Way look like a small suburb, while M87 is the sprawling capital city of the cosmos. Astronomers first catalogued M87 more than 2 centuries ago, when Charles Messier was charting faint smudges in the sky. To him, it was just another object that might confuse comet hunters, something to note and move on. Yet in the centuries since, M87 has revealed itself to be so much more. This is a giant among giants, a gravitational anchor in the Virgo cluster, pulling in smaller galaxies, swallowing material and shaping the very landscape of its cosmic neighborhood. At the core of this galaxy lies a supermassive black hole of truly staggering proportions. It is not just large by human standards, or even by cosmic standards. Astronomers estimate that the black hole at M87's heart contains the mass of more than 6 billion suns. For perspective, the black hole at the center of our Milky Way, Sagittarius A star, is huge by itself, yet it is about 1,000 times smaller. What dwells in M87 is almost beyond comprehension, a deep well of gravity that dominates everything around it. This black hole is no quiet prisoner of the galaxy either. It makes its presence known in dramatic fashion. From its core, a jet of high-energy particles erupts into space, stretching thousands of light-years like a cosmic beacon. First spotted in the early 20th century, this jet was one of the first real clues that something extreme and unseen was powering galaxies. What we now understand is that matter falling toward the black hole is heated and twisted by magnetic forces before being hurled outward at nearly the speed of light. The result is a jet so powerful that it can outshine entire galaxies in radio and X-ray wavelengths. Even from our distant vantage point, that jet remains one of the most striking features in the night sky. The sheer mass of M87's black hole raises fascinating questions about how galaxies and black holes grow together. Did the galaxy become so massive because it fed its black hole? Or did the black hole swell to its enormous size because it had such a vast galaxy to draw from? Astronomers are still working to untangle this mystery. What is clear is that M87 represents an extreme case, where both the galaxy and its central black hole have grown to scales far beyond the ordinary. The size of M87 is such that even light itself takes extraordinary amounts of time to cross it. The galaxy spans more than 120,000 light-years, meaning a beam of light would take longer than the entire history of human civilization just to travel from one side to the other. Within that span, untold numbers of stars live and die. Supernovae erupt like cosmic fireworks, while new stars form in gas clouds, though less so than in smaller galaxies. The black hole consumes matter in its central region, while the outer halo drifts quietly in the dark. From afar, it seems frozen, but within, it is a place of endless activity. It is fitting, perhaps, that M87 was chosen in 2019 as the galaxy whose black hole would be imaged for the first time. When the Event Horizon Telescope, or EHT team, revealed that glowing orange ring, the shadow of the black hole itself, it was not just a scientific milestone, it was a cultural one. For the first time in human history, we could see the outline of the unseeable, captured from a galaxy 55 million light-years away. That image did not only confirm Einstein's theories, it connected us to M87 in a way no words alone could. The Colossus in Virgo had shown us its heart. A galaxy built on giants, globular clusters and stellar populations in M87. In most galaxies, globular clusters are relatively rare. These are enormous, tightly packed spheres, each containing hundreds of thousands, sometimes even millions, of suns. Seen through telescopes, they appear like glittering orbs, each one shining with the light of stars that were already burning brightly long before Earth was even formed. For astronomers, they are records of the past, cosmic fossils that preserve information about how galaxies like M87 grew and changed across billions of years. Our Milky Way, for example, hosts about 150 of them. That number may seem impressive, but compared to the scale of M87, it is modest. M87 contains more than 12,000 globular clusters, an astonishing swarm of ancient stellar families orbiting in all directions around the galaxy. It is as though M87 is not just a galaxy, but a city built upon thousands of smaller, older communities, each with its own history. This enormous population of clusters is one of the key features that makes M87 so exceptional and so important to study. Globular clusters are some of the oldest surviving structures in the universe. Many of them formed more than 10 billion years ago, at a time when the universe was still young and galaxies were only just beginning to assemble. Because of their age, they act like snapshots of the early cosmos. By studying their stars, astronomers can learn about the conditions that existed when galaxies were first forming. The chemical makeup of these stars, for instance, tells us what elements were available at the time. Since heavier elements are forged in supernova explosions, a star's composition can reveal how many generations of stars lived and died before it was born. In globular clusters, most stars are poor in heavy elements, which means they are extremely ancient, born before the universe had much time to enrich itself with metals. The fact that M87 has more than 12,000 of these clusters suggests something important about its past. This galaxy has been a collector, a builder, and at times a destroyer. To gather so many globular clusters, M87 likely grew by merging with many smaller galaxies over billions of years. Each time one of those galaxies fell into M87's gravitational grasp, it left behind its clusters as souvenirs. Over time, those clusters became part of M87's extended family, orbiting in a vast halo that now stretches hundreds of thousands of light-years into space. In this way, M87's globular clusters are living evidence of the galaxy's violent and dynamic history, each one a remnant of a smaller world consumed by a larger one. Astronomers have noticed that the globular clusters in M87 are not all the same. Some are larger, some smaller, some are richer in heavy elements, while others are poorer. This diversity points to multiple waves of formation. Some clusters likely formed within M87 itself, perhaps in the chaotic early days when clouds of gas collapsed to form stars in bulk. Others came from outside, carried in by galaxies that M87 swallowed whole. By carefully measuring the colours, brightness and chemical fingerprints of these clusters, astronomers can piece together the story of how M87 grew. In smaller galaxies, globular clusters are rare jewels. In M87, they form an entire system of their own. Their orbits trace the mass of the galaxy, allowing astronomers to measure just how heavy M87 really is. When scientists track the motions of thousands of globular clusters around M87, they find that the galaxy's gravity is immense, so immense that it cannot be explained by stars and gas alone. The clusters reveal the presence of dark matter, the invisible scaffolding that holds galaxies together. Without these clusters as traces, it would be far harder to map the full mass of M87 and to understand its place in the cosmos. In deep images taken by the Hubble Space Telescope, the space around M87 is filled with tiny points of light, each one a separate globular cluster glowing faintly against the background. It is a view unlike that of almost any other galaxy. While most galaxies may have a halo with a few scattered clusters, M87's halo is swarming with them, as if the galaxy is wrapped in a glittering cloud. The stars within the clusters themselves also hold secrets. They are stable, long-lived stars, many of them smaller and cooler than our Sun. Because of their stability, they have been shining steadily for billions of years. Studying them helps astronomers test theories of stellar evolution. The fact that these stars are still visible today means that the clusters have survived countless galactic events, collisions, tidal forces, and the violent environment around M87's massive black hole. Their survival is remarkable, and it tells us that globular clusters are among the most resilient structures in the universe. Some astronomers suspect that M87's enormous collection of globular clusters may also point to its role as a central galaxy in the Virgo cluster. In many galaxy clusters, the central galaxy tends to be the largest and most massive, often hosting an unusually rich population of clusters. M87 fits this pattern perfectly. As the gravitational center of the Virgo cluster, it has had billions of years to pull in material from its neighbors. The clusters may be a record of that process, evidence of M87's dominance over its surroundings. In a way, they act like trophies, each one representing a smaller galaxy that M87 absorbed into itself. Why does M87 have so many more than other galaxies? Is there a natural upper bound to how many a galaxy can collect? Or is M87 simply an extreme example of a process that might occur in many other places we have not yet studied closely? These questions drive astronomers to look for more galaxies like M87, to see whether its huge population of clusters is unique or just one of many such cases. So far, M87 remains exceptional, a galaxy whose swarm of clusters has few rivals. On their own, each cluster is just a gathering of stars, but taken together, they reveal the grand history of M87, its violent mergers, its relentless growth, and its central role in the cosmic landscape. To look at M87's globular clusters is to see a record of billions of years written not in stone or parchment, but in the steady glow of ancient stars. The core mystery, tracing early clues of an invisible monster. When astronomers first looked closely at the center of Messier 87, they saw something that did not make sense. Unlike the gentle glow of most elliptical galaxies, M87's heart was bright, energetic, and unpredictable. It gave off radiation that stretched across the spectrum, from radio waves to high-energy X-rays, and it seemed to pulse with a hidden power. Something was happening in the shadows of this massive galaxy. The first real clue came from the way stars near the core were moving. In a normal galaxy, stars orbit the center in relatively calm, predictable paths. But in M87, many of the stars close to the nucleus were racing at astonishing speeds, some moving at hundreds of kilometers per second. To sustain such orbits, there had to be a tremendous amount of mass pulling on them from the very center. The gravitational pull needed to explain those motions pointed to something extraordinarily heavy and compact hidden in the core. Astronomers did not yet have a name for it, but the evidence was pointing to what we now recognize as a supermassive black hole. At the same time, radio telescopes began detecting a powerful jet of energy shooting out from the heart of M87. This jet, first seen in the early 20th century, stretched thousands of light years into intergalactic space. To produce such a structure required a tremendous engine, one capable of accelerating matter to nearly the speed of light. Normal stars could not provide that kind of power, nor could even the combined light of an entire galaxy. The jet was too focused, too energetic, to be anything but the signature of something extraordinary. For decades, astronomers debated its cause, but the idea of a central black hole, feeding on matter and ejecting energy, gradually became the most convincing explanation. By the mid-20th century, advances in spectroscopy allowed scientists to measure more carefully the speed of gas clouds orbiting near M87's core. Their orbits required an object with billions of times the mass of the Sun packed into a space smaller than our solar system. There was no known natural object that could fit this description other than a black hole. The concept of a black hole had once been theoretical, even controversial. But here, in the center of M87, the evidence was becoming harder to deny. The jet itself became one of the most studied features of M87. When astronomers used radio telescopes to peer at it in finer detail, they discovered shock waves, knots of energy, and structures that seemed to twist and ripple as they moved outward. The jet was alive with motion. Matter inside the jet was moving at nearly the speed of light, and as it did so, it gave off radiation through a process known as synchrotron emission, light created when charged particles spiral around magnetic fields. What could launch and sustain such a jet for millions of years without running out of fuel? The answer, again, pointed to the steady feeding of a supermassive black hole. Through the 1960s and 1970s, the idea of black holes at the centers of galaxies began to gain traction. M87 became one of the prime candidates. Astronomers compared its activity to other galaxies with bright cores, known as quasars, which were even more luminous and distant. Though M87 was not as extreme as a quasar, its central engine seemed to operate on the same principle. The strongest evidence of all came in the 1990s, when the Hubble Space Telescope was used to study the motions of stars and gas very close to M87's center. Hubble's sharp vision allowed astronomers to track how fast material was orbiting at distances of only a few light years from the core. The speeds were staggering. Stars and gas clouds were whipping around as if caught in the grip of a compact object billions of times more massive than the Sun. No cluster of stars, no ball of gas, no exotic form of matter could remain stable with such density. The conclusion was unavoidable. Calculations suggested a mass of more than 6 billion suns. This cosmic monster could dominate the entire galaxy around it. The invisible monster that astronomers had long suspected was real, and it was more massive than almost any other known. As the evidence piled up, M87's central black hole became a focus of intense study. Radio observatories across the world turned their antennas toward it, trying to capture the fine details of the jet and the core. X-ray satellites observed its high-energy emissions, tracing the flow of matter as it spiraled inward. Every wavelength of light told part of the story, painting a picture of a system dominated by the hunger of a black hole. For decades, though, the black hole itself remained invisible. Its presence could be inferred, its effects measured, but the event horizon, the very edge of the black hole, remained hidden. Mass and scale of M87 star. The black hole at the center of M87, aka M87 star, represents a concentration of matter so enormous that it bends not only space and time, but our very ability to picture it. One way to try to grasp its size is by considering its event horizon, the boundary beyond which nothing can escape its gravity. For M87 star, this invisible surface would stretch so far that if placed at the center of our solar system, it would encompass everything out to the orbit of Pluto. Every planet, every asteroid, every icy body in the Kuiper belt would be swallowed inside that sphere of no return. Compared to stellar mass black holes, which are usually only a few kilometers across, this difference is staggering. The black hole at the heart of M87 spans about 40 billion kilometers in diameter. Astronomers often use the term supermassive casually, but M87 star forces a re-evaluation of what that word really means. Black holes, a few million solar masses in size, like the one at the center of the Milky Way, Sagittarius A star, are considered immense. Yet compared to M87 star, even Sagittarius A star seems modest. That difference in scale has real consequences for how these objects behave and how we can study them. One of the paradoxes of black holes is that the larger they are, the less extreme the environment just outside their event horizons becomes. Around a stellar mass black hole, gravity changes so rapidly over short distances that anything nearby would be torn apart in a process known as spaghettification. But around a supermassive black hole like M87 star, the gradient is gentler. A spaceship near its event horizon, in theory, would feel tides far less violent than those near a smaller black hole. That doesn't mean survival is likely. Radiation and other hazards would still be fatal. But it does mean that the physics operates differently at these giant scales. The sheer mass of M87 star also gives it a special place in astronomy. Its size makes it one of the few black holes that we can actually image, as demonstrated by the Event Horizon Telescope in 2019. While smaller black holes are far too tiny to resolve even with our most powerful telescopes, M87 star's event horizon is large enough, relative to its distance of 55 million light-years, to appear just barely within reach of Earth-based instruments. The famous orange ring image of M87 star exists precisely because of this balance. It is both massive enough and close enough to be studied in detail. Without its titanic scale, that achievement would not have been possible. Its gravitational influence also extends much farther than the event horizon. Stars at the very center of M87 orbit at extraordinary speeds. Gas clouds funnel inward, heated to millions of degrees as they spiral around the abyss. This furious activity produces radiation across the spectrum. The black hole's mass is the engine driving it all, converting the infall of matter into energy that spills out into space. The jet of M87 is perhaps the most dramatic expression of its power. While the precise mechanism is still debated, most models suggest that magnetic fields twisted by the rotation of the black hole play a key role. The enormous mass of M87 star makes the jet possible. Without a black hole of such scale, the stability and sheer length of the jet would be difficult to sustain. To appreciate the uniqueness of M87 star, it helps to put it in a galactic context. Supermassive black holes are thought to exist in the centers of most, if not all, large galaxies, but not all are so heavy. The Milky Way's Sagittarius A star is considered typical, while many galaxies host central black holes of a few million to a few hundred million solar masses. M87 star sits in the extreme upper range. Only a handful of known black holes surpass it, such as the ones in giant elliptical galaxies in massive clusters. Its size is partly a consequence of its environment. M87 lies at the heart of the Virgo cluster, one of the largest nearby collections of galaxies. Every time M87 absorbed another galaxy, its black hole likely merged with the intruders, adding to its mass. This slow accumulation over eons sculpted the titanic object we see today. Its enormous mass provides a natural laboratory for general relativity. The way light bends around its event horizon, the shape of its shadow, and the dynamics of the jet all provide opportunities to check whether Einstein's theory holds true under such extreme conditions. If there were ever cracks to be found in our understanding of gravity, a black hole like M87' is where they might appear. So far, the theory has stood firm, but the observations are still young. When astronomers say M87' is 6.5 billion solar masses, they are really pointing to a truth that transcends numbers. It is a reminder of how small we are in comparison. Our Sun, which seems overwhelming when we feel its heat on Earth, is barely a speck against the mass of this distant giant. The Cosmic Beacon, discovery of the M87 jet in 1918. In the spring of 1918, at the Lick Observatory in California, an astronomer named Heber Curtis was carefully photographing the galaxies of the Virgo cluster. Curtis was already familiar with faint, fuzzy smudges of light through telescopes, as this was an era when the debate over the true nature of galaxies, then called spiral nebulae, was still very much alive. But when he turned his attention to Messier 87, he saw something that stood apart from the rest. From the heart of the galaxy extended a strange, linear feature that reached thousands of light years into space. It looked like a thin beam, sharply defined against the softer glow of the galaxy itself. Galaxies were only just beginning to be understood as immense collections of stars outside our own Milky Way. To see one that appeared to have a bright, straight ray shooting out of its nucleus was completely unexpected. Curtis himself described it as a curious straight ray in his published notes. There was nothing like it in any other galaxy he had studied, and no existing theory could account for it. Was this a trick of the telescope, perhaps an optical defect, or a background object aligned by chance? Or was it truly a structure belonging to M87? Subsequent observations confirmed that the jet was real. Over the decades, as instruments improved, astronomers kept returning to M87 to examine this mysterious feature. They found that it was not only a streak of visible light, but also a powerful emitter in other parts of the spectrum. In radio wavelengths, the jet blazed with even greater intensity, stretching farther than Curtis could have imagined with his early photographic plates. X-ray observations decades later revealed hotspots where particles within the jet were being accelerated to extraordinary energies. What made the 1918 discovery so important was that nothing in stellar physics could explain a straight, collimated beam of energy extending thousands of light years into intergalactic space. Whatever was driving the M87 jet had to be far more compact and far more energetic than a cluster of stars. By the middle of the 20th century, as the black hole hypothesis began gaining traction, the jet of M87 became one of its most compelling pieces of circumstantial evidence. Curtis's discovery, made long before the concept of a black hole was even formalized, turned out to be one of the first direct glimpses of what such a process might look like. As technology advanced, astronomers began to map the jet in astonishing detail. Radio telescopes showed that it extended well beyond the galaxy itself, reaching a length of more than 5,000 light years. Observations revealed knots and shocks along its length, where particles collided and energy was released in bursts of light. Curtis could not have known in 1918 what he was really looking at. The term black hole would not even be coined until the 1960s, and the first solid theories about supermassive black holes powering galactic centers would not arrive until decades later. Yet his observation of that thin streak of light was a seed that future generations of astronomers would return to again and again. With hindsight, we can see how crucial it was. Without the jet, M87 might have remained just another giant elliptical galaxy, impressive in size but not especially distinctive. With the jet, it became a place where the universe itself had constructed an experiment in high-energy astrophysics for us to witness. The spinning question, what we know and don't know about M87 stars' rotation. Black holes are not static objects. Like stars and planets, they can rotate, carrying with them the strange ability to drag space-time itself into a whirl. This rotation, or spin, is thought to be a fundamental property of black holes, alongside their mass and electric charge. Yet measuring it is one of the greatest challenges in astronomy. For M87 star, the clues are tantalizing but incomplete. We know it may be spinning, perhaps rapidly, but the details remain hidden behind the veil of the event horizon. When a black hole spins, it changes the environment around it in remarkable ways. Near the event horizon, the drag of space-time becomes so intense that nothing can remain still. Even light is forced to swirl in the direction of the spin. This region, called the ergosphere, creates opportunities for energy to be extracted from the black hole. The faster the spin, the more powerful this effect becomes. For M87 star, this possibility is especially important because it may help explain its enormous jet of plasma. The jet of M87 is highly collimated, meaning it stays narrow and focused even over intergalactic distances. To achieve such stability, something at the center must be acting like a cosmic engine. Many theories suggest that the black hole's spin is key. Magnetic fields twisted by rotation can act as channels, funneling energy outward. If M87 star is indeed spinning at a high rate, it could provide the raw force needed to power one of the most dramatic displays of astrophysical energy in the universe. But how do we know whether M87 star spins and how fast? Unlike mass, which can be inferred from the motions of stars and gas, spin does not leave such obvious imprints. Instead, astronomers look for indirect signs. One of the most important comes from the EHT image. Some parts of M87 star are brighter than others, a sign that material in the accretion disk is moving toward us at relativistic speeds, while other parts move away. The pattern of brightness and shape can, in principle, give hints about how the black hole is rotating. Models of the data suggest that M87 star could be spinning fairly rapidly, though the exact rate is still uncertain. Some estimates point to a spin close to the maximum allowed by physics, while others suggest a more moderate value. The truth is that the resolution and sensitivity of current observations are not enough to nail down the answer. The EHT gave us our first glimpse of a black hole's shadow, but details about spin remain buried within the noise. Future observations, with more telescopes and better data, may refine this picture. Even without a precise measurement, the very possibility of spin helps explain much of what we see. The jet's persistence across tens of thousands of light years points to a long-lived engine. A spinning black hole can provide that engine by continually channeling rotational energy into the surrounding plasma. Without rotation, it is hard to imagine how the jet could remain so stable for millions of years. The brightness asymmetry in the ring also suggests movement, consistent with the disk of material spiraling inward around a rotating object. Piece by piece, the clues point towards spin, even if the exact speed is elusive. Another intriguing aspect of spin is its role in shaping the growth of black holes. When matter falls into a black hole, it carries angular momentum with it. If material generally flows in from one direction, the spin of the black hole builds up. But if matter arrives chaotically from many directions over billions of years, the spin could slow or even change orientation. For a galaxy like M87, which has likely grown by devouring other galaxies, the history of mergers may have left a complicated imprint on its central black hole spin. Did it absorb other spinning black holes, adding to its rotation? Or did chaotic feeding disrupt a steady spin? Light paths near a rotating black hole bend differently depending on the direction of spin. The size and shape of the black hole's shadow are influenced by this effect. A rapidly spinning black hole can make the shadow appear slightly smaller in certain orientations. Detecting these subtle changes requires extreme precision, but the theory is clear. The spin of a black hole leaves fingerprints on the light we see. If future observations can sharpen the image of M87's ring, astronomers may be able to decode those fingerprints and reveal its spin rate. Magnetic fields on the edge of oblivion. Magnetic fields, those unseen lines of force that guide compasses on Earth and protect our planet from solar winds, take on a role that is almost mythic near the event horizon of a black hole. Around M87, these fields are thought to be sculptors, bending matter and twisting energy. Unlike the familiar pull of gravity, which dominates our sense of what a black hole is, magnetic fields are elusive, hard to detect directly. When astronomers trained the EHT on M87, they did not only capture the now famous shadow of the black hole, they also noticed patterns in the light that revealed polarization, a signature of magnetic influence. Light becomes polarized when it scatters or passes through a medium aligned in a certain way, and in the case of M87, this alignment hinted at the presence of structured magnetic fields threading the plasma around the black hole. It was as though the glowing gas near the event horizon carried with it a fingerprint, whispering that magnetic fields were at work in the chaos. The presence of magnetic fields in such an extreme environment is not a surprise in itself. Charged particles, by their very nature, create and respond to magnetic fields. But the way these fields persist, strengthen and shape the plasma near a black hole is still mysterious. Near M87, gravity should dominate so completely that everything else is almost irrelevant. Yet the jet that erupts from the center tells another story. Something is resisting the all-consuming pull, redirecting material and energy not into the abyss, but outward into space. The magnetic fields may be the key to this apparent defiance. To understand the importance of these fields, it helps to imagine the black hole not as a passive sink, but as a rotating dynamo. This rotation, coupled with the surrounding plasma, can twist and amplify magnetic fields. Polarization maps produced by the EHT gave us the first real evidence of this process. When researchers compared the polarized light around M87 to theoretical models, they found striking agreement with scenarios where strong, ordered magnetic fields are present. These fields appeared to be aligned in a way that suggested they were shaping the flow of matter near the event horizon, confining it, perhaps even preventing all of it from being swallowed. Instead, part of that matter was being redirected and accelerated outward. The jet that M87 is famous for suddenly seemed less like a mystery and more like the inevitable outcome of magnetic precision. Yet the details remain frustratingly complex. Magnetic reconnection, turbulence, plasma instabilities, all the messy, unpredictable behaviours of charged particles still play out on scales far too fine for us to observe directly. Astronomers and physicists rely on simulations, feeding supercomputers with equations that model the interplay between gravity, plasma, and magnetic fields. These simulations suggest that near the edge of the event horizon, magnetic fields can build up to extraordinary strengths, becoming what theorists call magnetically arrested. In this state, the field is so powerful that it chokes off the inflow of matter, forcing it to spiral along magnetic lines rather than plunge freely inward. What emerges from this delicate balance is a release valve where energy and matter escape. The possibility that M87' is a magnetically arrested disk, what researchers shorten to MAD, has become one of the leading explanations for the galaxy's jet. If true, it means that magnetic fields are decisive players in black hole evolution. They dictate how much matter is consumed, how much is ejected, and how the black hole communicates with the galaxy around it. For a phenomenon that cannot be seen directly, their influence is immense. Without jets, galaxies themselves might look very different. They act as regulators, heating intergalactic gas, slowing down or even stopping new stars from forming and altering the balance of cosmic ecosystems. The EHT's polarized image of M87' may seem faint compared to the dramatic orange ring that captured headlines, but for scientists, it is arguably the more profound revelation. It tells us that we are beginning to see not just the silhouette of the beast, but the machinery that makes it roar. Still, we are only at the beginning of understanding. What is the exact strength of these fields? How do they fluctuate over time? Are they stable, ordered structures, or do they thrash and twist in constant turbulence? If magnetic fields can be understood here, at this immense scale, they may provide a unifying thread that explains jets across the cosmos, from stellar mass black holes in our own galaxy to the monstrous giants at the centers of distant quasars. The black hole as a cosmic power plant. Gas and dust, once captured by a black hole, do not simply fall inward in a straight plunge. Instead, they form an accretion disk, a swirling structure where friction and turbulence grind particles together at immense speeds. This violent churning heats the material to temperatures of millions of degrees. To the outside observer, this makes the surroundings of a black hole one of the most radiant objects in the universe. In fact, the efficiency of this process surpasses that of nuclear fusion, the engine that powers stars. While the fusion reactions in the core of our Sun convert less than 1% of mass into usable energy, matter spiraling into a black hole can release up to 10% or more of its mass energy before vanishing. That staggering figure is why black holes, though dark at their core, are capable of powering entire galaxies. In the case of M87', the accretion disk is not only bright, but also chaotic. Magnetic fields thread through the plasma, dragging material into vortices. Every atom that drifts too close becomes part of a vast energy conversion system. Its gravitational potential energy is extracted and released as radiation. It is worth pausing to consider just how efficient this is compared to any energy source we are familiar with. If 1 kilogram of matter is consumed by fusion, as happens in the Sun, the energy released is enormous by human standards. Yet if the same kilogram were to fall into M87', the energy liberated before its final disappearance would be an order of magnitude higher. Quasars, some of the most luminous objects in the universe, are powered by nothing more exotic than this process on a large scale. M87' in its youth likely blazed as one, its accretion disk converting matter into torrents of light that could be seen across billions of light years. The notion of a black hole as a cosmic power plant is not just a metaphor. Physicists have developed detailed models to describe how this energy extraction works, and the mathematics supports what observations reveal. The closer matter spirals to the event horizon, the faster it moves, approaching relativistic speeds. Collisions and turbulence in this high-speed plasma dissipate vast amounts of energy, radiating outward before the material vanishes. The inner edge of the accretion disk marks the boundary of maximum efficiency. Here, every swirl and shockwave is amplified by the immense gravity, squeezing the last possible photons from matter before it is consumed. At the same time, the black hole's spin adds another layer to the process. Frame dragging can be harnessed to extract even more energy. In 1969, physicist Roger Penrose proposed a theoretical process in which particles interacting in the ergosphere, the region just outside the event horizon, could actually emerge with more energy than they entered, drawing rotational energy from the black hole itself. Later refinements, particularly the Blandford-Snijek mechanism, extended this idea to explain how magnetic fields anchored in the accretion disk could tap into the black hole's spin. In other words, M87' may not only be converting matter into energy through infall, but also siphoning its own rotational energy into the colossal jet we see today. The jet from M87' carries as much energy as 100 million supernova, all sustained by the constant infall of matter and the black hole's spin. This energy is not locked away. It has tangible effects, sculpting the interstellar and intergalactic environment. On Earth, when we think of power plants, we imagine machines designed to control energy production. Black holes, by contrast, are not designed, yet they embody the same principle on a vastly grander scale. Efficiency, output, and regulation all occur naturally through the interaction of gravity, plasma, and magnetic fields. If humans could one day harness even a fraction of this process, the energy needs of civilizations would be met for eons. Theoretical proposals about advanced alien civilizations often imagine them using black holes as ultimate power sources, a concept sometimes called black hole farming. While speculative, the idea stems directly from the reality we observe, that nothing in the universe extracts energy as effectively as matter falling into a black hole. Observations from the EHT and other instruments continue to refine our grasp of how accretion flows operate, how jets are launched, and how much energy can realistically be extracted. Each new dataset tests the models, and each discrepancy forces researchers to reconsider the details of plasma physics under extreme conditions. The goal is not only to explain M87', but also to develop a universal framework for black hole power generation across the cosmos. Particles at near light speed. What powers the jet? When Heber Curtis first photographed the jet of M87 in 1918, he could not have guessed that what appeared as a faint streak of light was in fact a stream of matter moving at nearly the speed of light. Only in the decades that followed, with advances in radio astronomy and high-energy astrophysics, did the true nature of the jet begin to come into focus. The narrow beam is not simply a shaft of light, but a torrent of charged particles, electrons, and possibly heavier particles accelerated to relativistic speeds. One leading idea to explain this process is known as the Blandford-Snijek mechanism, first proposed in 1977. In this model, the black hole's rotation is the key ingredient. If magnetic field lines thread through the accretion disk and into the ergosphere, then energy can be extracted from the black hole's spin. The magnetic fields act like wires in a cosmic dynamo, converting rotational energy into kinetic energy and launching particles outward at relativistic speeds. The jet, in this view, is not just a byproduct of accretion, but a direct channel through which the black hole's own energy is tapped. Another model, sometimes considered alongside or in combination with Blandford-Snijek, is the Blandford-Payne mechanism. This theory emphasizes the role of the accretion disk rather than the black hole's spin. Magnetic field lines anchored in the disk can sling matter outward if they are inclined at the right angle. In this sense, the disk acts like a launching pad, with magnetic fields providing the tension and torque needed to accelerate material. The particles then spiral along these field lines, forming the narrow beam we observe as the jet. While the Blandford-Payne process does not directly require the black hole's spin, it relies on the complex interplay between the inflowing plasma and magnetic fields. In reality, both mechanisms may be at work, their effects combining to sustain the jet of M87 over thousands of light years. Using very long baseline interferometry, astronomers can resolve the base of the jet on scales of light days. bringing us remarkably close to the black hole. These studies show that the jet appears collimated almost immediately after it emerges. That level of precision suggests that the launching mechanism is tightly bound to the black hole's gravity and magnetic environment, supporting the idea that the jet is linked to the event horizon and the ergosphere. Furthermore, polarization measurements from the EHT reveal that light from the accretion disk and jet is polarized in a way consistent with strong magnetic fields threading the plasma. But while we know that magnetic fields and rotation play key roles, many details remain uncertain. For instance, the exact composition of the jet is still debated. Is it made primarily of electrons and positrons, the antimatter counterparts of electrons, or does it also include protons and heavier ions? The answer affects how we calculate its energy and how we understand the processes that accelerate it. If the jet is mostly leptonic, electrons and positrons, it may be easier to explain its radiation signatures, since lighter particles are more readily accelerated. If it is baryonic, containing heavier particles, then the jet carries far more mass and energy than currently assumed. M87, with its brightness and proximity compared to more distant quasars, offers a rare chance to disentangle these possibilities. The jet also provides insight into how energy flows outward from a black hole. High-resolution images show knots along the jet's length, regions where shocks or instabilities compress the plasma and trigger bursts of synchrotron radiation. These knots suggest that the jet is a dynamic structure shaped by interactions with the surrounding medium. Each bright knot mimics processes that occur in cosmic rays and other high-energy astrophysical environments. In this way, the jet is not only a probe of black hole physics, but also a testing ground for the physics of plasmas in general. From its launch point, the jet extends without dispersing into the intergalactic medium. This remarkable stability suggests that magnetic fields act like a skeletal framework, keeping the plasma collimated as it travels. Simulations show that without such fields, jets should flare out and dissipate quickly. Yet M87's jet holds together, a cosmic spear piercing the void. The energies involved in this process are staggering. Particles in the jet are accelerated to Lorentz factors of several million, meaning they travel so close to the speed of light that time itself slows for them compared to an outside observer. These relativistic speeds explain why the jet shines so brightly, as the spiraling of near-light speed electrons around magnetic fields produces emission across the spectrum. In some regions, the jet also glows in X-rays, evidence that particles are being pushed to even higher energies than previously thought. M87, therefore, offers us a front-row seat to some of the most extreme particle accelerators in the universe, outstripping anything humans could ever build on Earth. How much energy comes from the spin versus the disk? What is the jet's true composition? How does it remain stable over cosmic time? The answers lie hidden in the light we receive, in the flickers, polarizations, and spectral signatures that tell the story of particles racing at nearly the speed of light. How black holes shape galaxies. The jet of Messier 87 interacts with its surroundings in ways that stretch across tens of thousands of light years, and its effects ripple through the galaxy and beyond. When astronomers speak of feedback, they mean this cycle of influence, where the black hole at a galaxy's center both consumes matter and at the same time returns energy back into its environment. This energy is not gentle. It is released as radiation, winds, and most dramatically, as relativistic jets like the one we see in M87. These forces can shape the life of a galaxy, steering its growth, altering its structure, and even deciding how many new stars will ever form within it. In the case of M87, the jet serves as a clear example of feedback in action. This enormous outflow plows into the galaxy's interstellar medium and into the hot gas of the Virgo cluster that surrounds it. The result is like a cosmic blowtorch. Vast bubbles and cavities are carved into the surrounding plasma, regions where the jet's energy has swept material aside. Astronomers can see these cavities in X-ray images, where the otherwise smooth glow of hot cluster gas is broken by darker patches, silent records of the jet's violence. The scale of this feedback is staggering. The amount of energy carried by M87's jet is comparable to the combined output of billions of stars. But unlike starlight, which radiates in all directions, the jet is focused, and as it collides with surrounding gas, it stirs turbulence, drives shock waves, and prevents the gas from cooling and condensing into stars. This is a crucial effect, because without it, M87's vast reservoirs of hot gas might have formed new generations of stars, potentially changing the character of the galaxy. Instead, much of that gas remains in a heated state, unable to collapse, locked away from star formation. This is not just a detail of M87, it is part of a broader story in cosmology. Astronomers have long puzzled over why massive galaxies like M87 do not contain as many young stars as their gas content would suggest. The answer seems to be that black holes act as regulators. Left unchecked, a giant galaxy might become a runaway factory of star formation. But the central engine, through feedback, dials down the process. It prevents galaxies from growing endlessly and keeps the balance between black hole and galaxy in check. In M87, the evidence for this regulation is especially visible. Observations with the Chandra X-ray Observatory have revealed enormous lobes of hot gas inflated by the jet. These lobes extend tens of thousands of light years from the center and contain enough energy to offset the cooling of the cluster gas for hundreds of millions of years. It is as though the black hole is reheating its surroundings over and over, making sure the gas cannot settle into the calm conditions needed for new stars to ignite. This process is sometimes called maintenance mode because it prevents further galactic growth while sustaining the balance we see today. What makes M87 such a valuable case is the sheer clarity of its feedback signatures. In many galaxies, the effects are subtle or hidden by dust and distance. But M87's proximity, size, and activity allow astronomers to trace the entire sequence. They can connect the physics near the event horizon to the bubbles floating in the cluster gas. This chain of cause and effect provides a direct look at the co-evolution of galaxies and their central black holes. Why do black holes and galaxies grow together in such a tightly linked way? Observations show that the mass of a galaxy's central black hole is correlated with the overall size of its bulge of stars. This is surprising because the black hole itself is tiny compared to the galaxy, only a fraction of the total mass. Yet the relationship holds across galaxies large and small. M87 demonstrates why even a relatively small region of intense gravity, when it releases energy through feedback, can influence the entire galaxy. In this sense, M87 star acts like a thermostat, regulating its host's long-term development. M87 sits in the heart of the Virgo cluster, surrounded by thousands of other galaxies, all immersed in a sea of hot, tenuous gas. The jet's energy does not stop at M87's borders. It spills into this larger environment, stirring the cluster medium and shaping the conditions under which other galaxies evolve. In this way, the activity of one supermassive black hole can ripple across cosmic neighborhoods, influencing the growth of structures on scales far larger than itself. Astronomers use terms like feedback cycle and IGN heating to describe this. M87 star is actively sculpting the future of its surroundings, dictating how matter can or cannot transform into stars, and setting the pace for galactic life. The jet is only the most obvious part of this feedback. The invisible shock waves and heat reservoirs left in its wake are equally important, silent but lasting imprints of the black hole's control. The telescope the size of Earth, The EHT network explained. To see the heart of Messier 87, astronomers faced a problem of scale that almost defied imagination. They were trying to capture an image of a black hole's event horizon, a region so small on the sky that it appeared no larger than a donut on the surface of the Moon seen from Earth. Ordinary telescopes, no matter how large, simply could not resolve something so minuscule at a distance of 55 million light-years. A new approach was needed, one that would not rely on building a single giant dish, but instead on combining the power of many observatories spread across the globe. This idea became the Event Horizon Telescope, a project that stitched together the eyes of Earth into one vast instrument. The principle behind the EHT is simple to state, but difficult to achieve. The resolving power of a telescope depends on its size. The larger the diameter, the finer the details it can see. To resolve the shadow of M87', astronomers calculated that they would need a telescope effectively the size of Earth itself. Of course, no single dish that large could ever be built. Instead, scientists turned to a technique called Very Long Baseline Interferometry, or VLBI. In this method, radio signals collected by different telescopes are combined in such a way that the array behaves like one enormous telescope, its mirror stretched across continents. The participating observatories span some of the most remote and extreme environments on the planet. Dishes in the deserts of Chile, the volcanic summits of Hawaii, the frozen tundra of Greenland, and the high plateaus of Spain and Mexico all contributed to the network. Each site was chosen not just for its equipment, but for its ability to work in sync with others, creating baselines thousands of kilometers long. The farther apart the telescopes, the higher the resolving power, and the closer astronomers could come to approximating that impossible Earth-sized dish. The challenge, however, was not just in pointing these telescopes at the same target, but in uniting their observations with exquisite precision. Radio waves from M87' arrive at each dish at slightly different times, down to fractions of a billionth of a second. To combine the signals correctly, the timing had to be recorded with atomic clocks accurate to within a few trillionths of a second. Every observatory in the EHT network was equipped with such clocks, ensuring that when the data were later combined, the wavefronts from the black hole would align as though caught by a single instrument. Observing M87' meant collecting petabytes of raw information, far too much to transmit digitally over the internet. Instead, the signals were stored on hard drives, which were then physically flown to central processing centers. There, teams of scientists used powerful supercomputers to synchronize and stitch together the signals from each telescope. This process is where the illusion of an Earth-sized dish truly comes to life, the scattered observations merging into a single, coherent image. The EHT observes at 1.3 millimeters, a band in the radio spectrum that can penetrate the dust and gas near the black hole. Shorter wavelengths like visible light would be scattered and longer wavelengths would blur the details. But working at millimeter wavelengths requires extraordinary precision in instrumentation and observing conditions. Even the water vapor in Earth's atmosphere can distort or block the signals. That is why many of the EHT sites are located at high altitudes, where the air is thin and dry. For several days at a time, telescopes across the globe must point at the same patch of sky, record data simultaneously, and remain stable in their performance. Weather at just one site can affect the quality of the whole network. The result is a logistical effort as challenging as the science itself, with teams waiting for narrow observing windows when all the conditions align. When the data are finally combined, they do not produce an image in the traditional sense. Instead, they yield interference patterns, complex ripples that must be translated into pictures using algorithms. Multiple teams work independently on this step, ensuring that the results are not artifacts of any single method. The now famous ring of light surrounding the shadow of M87' emerge not from a single photograph, but from the careful reconstruction of countless radio wave correlations, tested and confirmed by different approaches. The event horizon of M87' appears to be about 40 micro-arc-seconds across. That is like trying to read the date on a coin in New York while standing in Paris. No optical telescope, no matter how advanced, could achieve that resolution. Only by turning Earth itself into a platform for interferometry could astronomers hope to succeed. The Event Horizon Telescope represents not just a technical achievement, but a shift in how humanity observes the universe. Instead of building larger and larger single instruments, it harnessed the collective power of many, uniting them into something greater than the sum of their parts. The black hole was revealed by a collaboration that spanned the globe, each dish and each scientist contributing to the effort of making the invisible visible. New telescopes are being added to the network, expanding its reach and improving its sharpness. Future campaigns will not just capture still images, but movies of matter swirling around black holes, showing how these extreme objects change in real time. The vision of an Earth-sized telescope is now a proven reality, one that has already transformed our understanding of the universe and promises to go further still. Challenges of synchronization, atomic clocks, and precise timing. When scientists set out to build the EHT, they knew that synchronizing observatories scattered across the globe would be one of the greatest hurdles. Unlike optical telescopes that can directly form images with mirrors, the EHT had to rely on radio signals collected at different sites. The success depended entirely on timing. If one telescope recorded the arrival of a wave even a tiny fraction of a second off from another, the interference patterns would blur and the entire image would collapse into noise. The entire project balanced on the ability to measure and preserve time with an accuracy that went beyond anything used in ordinary human activity. A radio wave arriving from M87' would strike each telescope at slightly different times depending on their position on Earth. The wavefront hitting Chile would not be the same instant as the wavefront reaching Hawaii or Spain. To reconstruct the wave as if Earth itself were one gigantic dish, astronomers had to know exactly when each signal arrived. Even an error of a few billionths of a second would distort the picture, because at the observing wavelength of 1.3 millimeters, the waves cycle hundreds of billions of times each second. To combine them properly, the system required clocks that could keep track of time with almost unimaginable precision. This is where atomic clocks came in. Unlike mechanical clocks that rely on gears or even quartz clocks that rely on the vibrations of crystals, atomic clocks measure time by monitoring the natural oscillations of atoms. Certain atoms, like cesium and hydrogen, vibrate at frequencies so stable and so predictable that they form the very definition of the second itself. These atomic transitions act like nature's ultimate metronome, beating with a consistency that does not drift, does not wear out, and does not depend on temperature or environment. By installing such clocks at every EHT station, astronomers could ensure that each observatory stamped its data with the same standard of time, down to trillionths of a second. Each telescope recorded its incoming radio signals along with this atomic time reference onto specialized hard drives. In effect, the data streams were not just raw waves from the black hole, but detailed records of exactly when each ripple in the signal reached the dish. Later, when the drives were shipped to the central processing centers, the supercomputers could align the signals with one another by comparing their timestamps. The atomic clocks made this possible, allowing scientists to reassemble the scattered bits of data into a coherent picture. Without this precision, the signals would have been hopelessly out of sync. Imagine trying to coordinate a choir spread across continents, each singer starting a note at precisely the same microsecond. If one singer is late by even a fraction of a beat, the harmony falls apart. Now replace singers with telescopes, notes with radio waves cycling hundreds of billions of times per second, and the choir with a globe-spanning array. This was the challenge the EHT faced. The atomic clocks turned Earth into a coordinated listening device, each site contributing a perfectly timed piece of the cosmic symphony. Maintaining this synchronization was not easy. Atomic clocks, though extraordinarily stable, still needed to be monitored and calibrated. Engineers had to make sure that each one was functioning properly at high-altitude sites, some of them in extreme climates where equipment could be stressed by cold, heat, or thin air. Power supplies had to be stable, and the entire timing system had to remain insulated from electronic interference. Even minor disruptions could compromise days of observing. It was a delicate balance between cutting-edge science and practical engineering, where teams had to make sure that every clock, every drive, and every cable held steady during the coordinated campaigns. The precision of timing also shaped when and how observations could be made. All participating telescopes had to observe the black hole at the same time, with their clocks aligned and their instruments recording. This meant that equipment failures at a single site could threaten the entire dataset. The atomic clocks allowed for flexibility in the later stages, since data could be combined after the fact. But during observation, every site had to be locked in step. The coordination extended beyond technology into the realm of global teamwork, with dozens of institutions and hundreds of scientists depending on synchronization, not just of machines, but of people. Once the hard drives reached the correlators, the importance of timing became even clearer. The supercomputers used the clock signals to line up the data streams, shifting them back and forth by tiny amounts until the interference fringes emerged. These fringes, the patterns created by overlapping radio waves, contained the information that could be reconstructed into an image. If the timing marks had been inaccurate, the fringes would not appear, and there would be no way to extract the structure of M87'. The image of the black hole's shadow that the world saw in 2019 rested on these hidden time signatures. Timekeeping has always been tied to exploration. Sailors once relied on accurate clocks to find their way across the oceans. In the case of the EHT, atomic clocks guided humanity across a much larger ocean, the gulf of space between Earth and a distant galaxy. They turned scattered observatories into one instrument by mastering the flow of time. Each telescope alone could see only a blur. Together, bound by atomic time, they created clarity out of chaos. Petabytes of shadows, handling the data deluge. Light from the black hole did not produce an image as it would with an ordinary camera. Instead, each telescope gathered raw signals, recording the faint whispers of radio waves that had travelled for 55 million years before reaching Earth. The challenge was that these signals needed to be compared with one another in exquisite detail, requiring that every tiny fluctuation in the data be preserved. What resulted was a mountain of information, petabytes upon petabytes, far more than could ever be handled through ordinary networks or even the most powerful internet backbones available. The EHT relied on radio interferometry, but this technique does not simply add up signals. It depends on correlating them with astonishing precision. Because of this, none of the data could be compressed or transmitted in a convenient stream. Every wave, every fluctuation had to be preserved exactly as captured. That is why the collaboration ended up generating raw datasets that were measured not in gigabytes or terabytes, but in petabytes, millions of gigabytes of radio wave imprints. The internet, for all its speed, was helpless in the face of such a deluge. Even if the EHT had tried to transmit the data across cables, it would have taken years for everything to arrive. Instead, the solution was surprisingly old-fashioned: physical transportation. Massive racks of hard drives, each packed with the recordings from a given telescope, were carefully removed, stored and flown across continents in passenger airplanes. In some cases, it took weeks before all of the data from a single observing run was gathered together in one place, simply because of logistical hurdles. It was an extraordinary reminder that in the 21st century, there are still frontiers where physical speed beats digital speed. The two main destinations for this data were processing centres in the United States and Germany. Once the drives arrived, they were fed into special supercomputers designed specifically for the job of comparing signals across multiple telescopes. These correlators had to sift through the petabytes of raw recordings, aligning them in time, correcting for the curvature of Earth and compensating for differences in atmospheric conditions. Every telescope's data had to be adjusted and rechecked so that the faint signal from M87' could emerge from beneath the noise. Only after this enormous computational effort did the beginnings of an image start to appear. The fact that these signals survived the journey at all is another marvel. The radio waves that telescopes captured were already unimaginably faint, so faint that a passing truck near one of the observatories or even a gust of wind rattling an antenna could mask them. The raw recordings, therefore, had to be carefully protected from corruption. A single damaged hard drive could mean losing irreplaceable pieces of the puzzle, because the entire image depended on having signals from as many telescopes as possible. Engineers and scientists worked hand in hand to safeguard every bit of information, double and triple checking that the physical drives survived shipping intact. The teams working on the image of M87' had to wait months before all of the pieces were finally assembled. Unlike in ordinary astronomy, where a telescope can sometimes produce a useful result within days of an observing run, the EHT required long stretches of waiting, coordinating and verifying. For the scientists involved, this was both frustrating and exhilarating. They knew that buried inside those hard drives was something no one had ever seen before: the shadow of a black hole. The sheer size of the data also speaks to the scale of the challenge. Achieving that level of clarity demanded staggering precision, and with it came staggering amounts of information. It is almost poetic that the attempt to capture something so immense required human beings to wrestle with something so immense in its own way. Data measured in petabytes, too vast to be easily grasped in the mind. On one hand, the EHT was a triumph of cutting-edge science, an international collaboration using atomic clocks, supercomputers, and global synchronization. On the other hand, the solution to moving its data was almost quaint: load up the hard drives, carry them into an airport, and fly them by hand to the places they needed to go. It is a reminder that sometimes progress depends as much on practical ingenuity as on raw technology. As those hard drives whirred in correlators, slowly unraveling their secrets, the scientists began to see the faint ring of light around M87'. Every pixel was built from the combined effort of people, machines and data streams travelling halfway across the globe in suitcases. The human collaboration behind the machine, a global scientific effort. Over 200 researchers worked within the Event Horizon Telescope Consortium, representing institutions on nearly every continent. These were not only astronomers peering into the night sky, but also experts in physics, computer science, data engineering, and electrical engineering. Some built instruments to sharpen the sensitivity of radio dishes. Others designed algorithms to piece together the torrent of raw information. Still others specialized in managing the logistics of synchronizing observatories located in remote deserts, on volcanic peaks, and at the South Pole. It was a project where no single discipline could claim dominance. Instead, progress was made only when expertise flowed freely across boundaries. The telescopes themselves spanned the globe. Each location had its own challenges, and with them came scientists uniquely suited to handle those challenges. In Chile's Atacama Desert, one of the driest places on Earth, teams worked in high-altitude conditions, enduring thin air and piercing sunlight to keep sensitive radio dishes operational. In Hawaii, at the summit of Mauna Kea, engineers braved the extreme cold of the mountaintop, while also working alongside local communities concerned about the use of sacred land. At the South Pole, researchers contended with isolation so complete that once winter arrived, the station was sealed off from the outside world for months. Every site demanded resilience, both technical and personal, from the people who operated it. Because the telescopes were scattered across the globe, the project required constant communication across time zones and languages. Teams in Asia would hand off updates to colleagues in Europe, who would then pass progress reports to groups in North and South America. This rolling wave of collaboration ensured that the project never truly paused. Somewhere at any given hour, someone was refining code, checking an instrument, or analysing a small slice of data. The black hole's image was stitched not only from radio signals, but also from the invisible threads of human connection tying scientists together across the planet. The human side of the project extended far beyond the technical work, negotiating access to observatories, securing funding from multiple governments and institutions, and resolving cultural and logistical hurdles all demanded diplomacy and patience. Building a telescope the size of Earth is not only a scientific challenge, but also a political one. Scientists had to convince agencies and stakeholders that the effort was worth the resources, and that sharing equipment for a collective vision would ultimately serve everyone's interests. This required trust, not only in the scientific goal, but also in each other. Trust was especially vital in the way the data were handled. Only by combining the raw information in a careful, unbiased way could the final image emerge. To ensure that the process was rigorous, the collaboration split into multiple teams, each working independently with the same data but using different algorithms and methods. None of these groups shared their results with one another until the end. This way, when their separate reconstructions all converged on the same ring-shaped structure, confidence grew that what they were seeing was real. Such caution and discipline required humility, as scientists had to resist the temptation to claim discovery too soon. Equally important were the quiet contributions that rarely made headlines. Graduate students wrote code to test calibration methods. Postdoctoral researchers spent long nights checking atmospheric corrections for tiny errors. Engineers repaired equipment in the field under difficult conditions, sometimes improvising solutions from spare parts when new hardware was unavailable. Each of these roles may have seemed small when viewed in isolation, but together they were indispensable. The image of M87 star is as much a mosaic of human labour as it is of light from a black hole. Once the image was ready, scientists had to present it not only to their peers, but also to the general public. They knew the unveiling would become a global event, and they worked carefully to explain what the picture represented and what it did not. The glowing ring was not a direct photograph in the traditional sense, but a reconstruction based on careful measurements. Still, it was an authentic view of the event horizon's shadow, and its meaning reached far beyond science. In press conferences and interviews, researchers spoke with pride, humility, and often emotion, knowing they were witnessing a turning point in humanity's understanding of the universe. What makes this collaboration even more striking is that it happened at a time when the world often feels divided. National borders, political disagreements, and cultural differences can seem insurmountable. Yet in the pursuit of capturing the shadow of a black hole, scientists from across the globe set aside those divisions. They shared resources, knowledge, and credit, driven by a collective desire to push the limits of human understanding. The EHT thus became not only a scientific instrument, but also a symbol of what is possible when people work together for a goal larger than themselves. Just as gas and dust spiral inward toward the center of M87 star, drawn by gravity into a single luminous whirl, the efforts of hundreds of people converged on one remarkable image. Each contribution added momentum to the project, until together they produced something that none could have achieved alone. The image of M87 star is more than a scientific milestone. It is also a testament to what can happen when the best of human ingenuity, persistence, and cooperation are brought to bear. Why timing the observations was critical. The technology was extraordinary, the coordination immense, the data handling staggering in scale, but all of it would have been meaningless if the sky itself did not cooperate. Unlike optical telescopes, which peer in visible light, the EHT operates at radio wavelengths that are especially sensitive to atmospheric water vapor. Clouds, storms, or even a thin veil of humidity could weaken or distort the signals. Because the network relied on perfect synchronization, the weakest link could compromise the entire chain. This meant that observing windows had to be chosen with extreme care. The EHT did not have the luxury of trying again on any given night. There were only certain times of year when M87 was high in the sky at multiple observatories at once. For a target this far away, astronomers needed to minimize atmospheric interference, so the galaxy had to be observed when it was positioned well above the horizon. This reduced the amount of atmosphere its faint signals had to travel through. The observing season was typically restricted to a short period in the Northern Hemisphere's spring, when weather conditions across the various sites offered the best chance of alignment. Even then, the odds were daunting. Imagine trying to plan a single picnic that requires cloudless skies in the Andes, the Hawaiian Islands, Spain, Arizona, Mexico, and Antarctica, all on the same day. In practice, this meant years of waiting for the right moment. The collaboration could prepare instruments, fine-tune algorithms, and test synchronization. But when it came to the final observations, the heavens dictated the schedule. The 2017 campaign that produced the image of M87 star was only possible because of a rare stretch of cooperative weather across the globe. Scientists held their breath in the days leading up to the observations, watching forecasts with the intensity of pilots preparing for a transoceanic flight. Each site had its own local concerns: winds at high altitude in Chile, snow on Mauna Kea, seasonal storms in Mexico, the brittle dryness of Spain's Sierra Nevada. All of these had to fall into place. The stakes were high because missing a window meant waiting another year. Coordinating such a massive global operation was not something that could be repeated at will. Each telescope's schedule had to be negotiated months or even years in advance, balancing the EHT's needs with those of countless other research projects. The South Pole telescope in particular was accessible only during limited parts of the year, when flights could reach the station before winter isolated it for months. If weather ruined the synchronized observing run, all that effort would be lost, and the next opportunity would not come until the following spring. This fragility of timing highlights the delicate nature of very long baseline interferometry. To simulate a telescope the size of Earth, all participating sites had to look at the same target at precisely the same time. Gaps in the chain cannot simply be filled in later. If one telescope is blinded by weather, its absence leaves a hole in the virtual telescope's surface, reducing the clarity of the final image. The metaphor often used is that of building a giant mirror. If too many pieces are missing, the reflection is distorted or lost entirely. Even with good weather, timing the observations demanded further coordination with natural cycles. The telescopes had to point at M87 when it was visible at night, free from the interference of the sun. But the EHT was not limited to darkness alone. Radio observations can technically occur during daylight. Still, solar interference could introduce noise, and careful scheduling was required to minimize it. In some cases, sessions were run at odd hours, with teams working through the night to catch M87 at its best position. For those at the South Pole, M87 never rose high above the horizon. which made their participation even more dependent on cooperative skies. When the weather aligned and the telescopes opened their eyes to the universe, the atmosphere in control rooms around the world shifted from anxiety to exhilaration. Data flowed onto hard drives, bit by bit, as teams monitored instruments for any sign of interference. Scientists could prepare for years, and still their fate would be decided by forces entirely beyond their control. Some described the experience as nerve-wracking. Others recalled the tension of watching radar maps and forecasts in real time, knowing that the effort of hundreds of people was balanced on whether a storm front shifted by a few miles. In those moments, the collaboration was united in suspense. When the data was finally secured, the relief was immense. The gamble had paid off. Clear skies across continents had gifted humanity the chance to see deeper into the heart of M87 than ever before. But the memory of how close it all was remained fresh for the scientists. It underscored the fragility of even the most ambitious human projects when they rely on the cooperation of nature. How do you photograph the unseeable? The notion of imaging something unseeable demanded precision in defining what was being sought. Astronomers did not expect to capture a traditional photograph with crisp edges and fine details. Instead, they aimed for a reconstruction of patterns in light intensity at radio wavelengths. The image would be statistical in nature, pieced together from sparse data points collected across the globe. It would not be a snapshot in the everyday sense, but rather the product of careful reconstruction, a synthesis of raw signals into a coherent picture. To the untrained eye, this might seem less like a photograph and more like an impression. Yet it would be no less real, because the features that emerged would directly reflect the physics of space-time around the black hole. For decades, the black hole had existed primarily in equations, simulations, and theory. Artists painted illustrations of what one might look like, usually glowing disks of fire around dark centers. Scientists could model how light would bend and predict what shapes might appear. But until the EHT, no one had actually seen such a structure with their own eyes. This meant that when data started to come in, researchers had to be cautious. Were they seeing the true silhouette of a black hole, or were they looking at artifacts of noise, weather interference, or processing assumptions? Unlike stars, which can appear steady over years, the material swirling around a black hole is dynamic. Bright spots flare, knots of gas orbit quickly, and shadows can shift in subtle ways over the course of hours. For M87 star, whose immense size means its orbiting gas moves more slowly than in smaller black holes, this variability was somewhat less severe, but still present. The EHT teams had to account for the fact that they were not freezing a static object in place, but trying to catch a snapshot of a turbulent, ever-changing scene. It was like photographing a candle flame that flickers constantly, only at a scale spanning billions of kilometers. The solution to this problem lay in patience and consistency. Observations had to be repeated over multiple nights, capturing as much data as possible in the hope that the underlying shadow would stand out from the noise of variability. Then came the algorithms, which sifted through the chaos, searching for persistent patterns. If the shadow of the black hole was real, it would remain, even as the glow of the surrounding gas shifted. This approach allowed scientists to gradually peel back the layers of randomness and see the enduring imprint of the event horizon itself. The phrase, photographing the unseeable, might suggest impossibility, but the story of M87 star shows that impossibility is often only a matter of perspective. A black hole emits no light, yet it leaves a shadow. That shadow may be distant, small, and easily lost in noise, but with the right tools and collective effort, it can be revealed. The interferometry trick, linking telescopes across continents. Interferometry is not a new idea. Radio astronomers have been using it since the mid-20th century to sharpen their views of distant objects. The technique relies on the simple fact that two telescopes observing the same source at the same time capture slightly different wave patterns due to their separation on Earth. When those signals are combined, the interference between the waves carries information about the source's structure. By increasing the distance between telescopes, known as the baseline, astronomers can dramatically increase the effective resolution, as though the telescope were as large as the separation itself. In theory, the farther apart the telescopes, the sharper the view. But scaling up this principle to a planetary network introduced difficulties beyond anything interferometry had tackled before. With only 2 or 3 telescopes, the technique was already complex. The EHT linked 8 major observatories and eventually more, each sitting in remote and often harsh locations. Every pair of telescopes created a baseline, and the network of baselines crisscrossed the Earth like a web. The geometry of this web determined how much detail could be reconstructed from the signals. The final image of M87' was, in effect, a puzzle assembled from many pieces, each piece born of interference patterns between pairs of telescopes. The mathematics underpinning interferometry is both elegant and demanding. Each telescope records not just the strength of the incoming radio waves, but their precise timing and phase, the relative position of the peaks and troughs of the waves. When 2 telescopes' recordings are brought together, scientists can line up the signals and see how they reinforce or cancel each other. From those interference fringes, details smaller than the width of the telescope's dishes can be teased out. Multiply this across an Earth-spanning network, and the effective aperture, the virtual lens, is as wide as the planet itself. However, interferometry does not deliver a finished picture like a camera. Instead, it produces patterns of data in what astronomers call the Fourier domain, an abstract space that represents different spatial frequencies in the image. To turn those patterns into something recognizable, scientists must invert the data mathematically, reconstructing the most likely image consistent with the interference measurements. The result depends not only on the quality of the data, but also on the algorithms and assumptions guiding the reconstruction. Multiple teams worked independently to reconstruct the image from the same interferometric data, using different methods to avoid bias. Some algorithms favoured smoother images, others allowed for sharper features. A machine learning approach was also used, training algorithms on thousands of synthetic black hole simulations so they could recognise patterns in the data. When the teams compared their results, a striking consistency emerged. All methods revealed a glowing ring with a dark centre, the telltale mark of a black hole's shadow. The convergence of independent efforts confirmed that the image was not an artefact of the method, but a real feature of the cosmos. For the technique to work, signals from telescopes thousands of kilometres apart had to be aligned to within fractions of a wavelength, often smaller than a millimetre. That required hydrogen masses ticking with stability down to billionths of a second at every site. Without such precision, the interference patterns would wash out and the signal would dissolve into noise. Since our planet rotates, the relative positions of telescopes change with time. What starts as one baseline at midnight becomes another an hour later. Rather than a hindrance, this rotation actually became a tool. It allowed the EHT to sample many different angles of the target as Earth turned, filling in gaps in the virtual telescope's coverage. This principle, called Earth rotation synthesis, is one of interferometry's greatest strengths. It meant that a few telescopes could, over hours of observation, simulate far more coverage than their fixed positions alone would allow. Interferometry is a triumph of human ingenuity. It takes advantage of the physics of waves and the geometry of Earth to extend our senses far beyond natural limits. It transforms the entire planet into a single instrument capable of probing the most extreme objects in the universe. and it shows that solving the greatest mysteries of the cosmos requires not only advanced machines, but also the clever linking of ideas across disciplines, across borders, and across continents. Data processing and image construction. When the EHT's network of radio dishes first turned its gaze toward M87', what came back were torrents of raw signals. The first step was to ensure that the data gathered could even be combined. Hard drives were flown to two central processing facilities, one in the United States and one in Germany. Once there, the data had to be carefully synchronized. The process of refining the image involved repeated cycles of testing, calibration, and simulation. Scientists would take their algorithms, run them on synthetic datasets mimicking black holes, and check whether the output matched the known input. If the reconstruction introduced artifacts, false spots, misplaced shadows, it meant the algorithm needed adjusting. This back-and-forth testing built confidence that when the methods were applied to real data, the resulting image would be trustworthy. It was not enough to produce a striking picture. The collaboration needed to know, with rigor, that the ring they saw was not a trick of the math. Once the independent teams had completed their reconstructions, they came together to compare results. Despite the differences in style, the core was unmistakable, a dark center surrounded by a luminous ring, brighter on one side. The overlap was too strong to be coincidence. To further strengthen the result, the teams combined their approaches, creating a consensus image that blended the robustness of multiple methods. This final step did not erase the individuality of the reconstructions. Instead, it distilled them into a single, reliable portrait of M87'. The diameter of the ring matched remarkably well with predictions from Einstein's general relativity. Decades earlier, theorists had calculated that a black hole of M87''s mass should cast a shadow about 42 micro-arc-seconds across in the sky. The reconstructed ring fell directly in line with those expectations, offering one of the strongest confirmations yet that general relativity holds true even under the most extreme gravitational conditions. The famous orange glow was not the actual hue of the black hole's surroundings, but a visualization choice. The EHT observes in millimeter radio wavelengths, far outside the range of human vision. To make the image interpretable, scientists mapped the intensity of the radio signal to a color scale, choosing warm tones to emphasize the heat and energy of the plasma swirling near the event horizon. The orange ring we recognize today is, in that sense, both a work of science and of communication, an effort to translate invisible signals into something the human eye and mind can grasp. Behind the creation of the image was also an immense computational effort. Even after correlation, the raw datasets were so vast that processing required specialized high-performance computing clusters. The algorithms were not casual scripts, but sophisticated pipelines, capable of handling terabytes of input and producing stable reconstructions. Debugging, testing, and refining these pipelines was itself a scientific challenge, requiring expertise not only in astronomy, but in statistics, signal processing, and computer science. By insisting on independent reconstructions, cross-checks with simulations and alignment with theoretical predictions, the scientists built a foundation of trust beneath the orange ring. What emerged was not only a picture but a careful declaration. This is what the universe allowed us to see, and we are confident it is real. The journey from raw signals to the ring of M87' was not a straight line, but a layered process of reconstruction, testing, and consensus. Each stage was essential, and each step carried the weight of history. The result may look simple, but behind its simplicity lies one of the most intricate chains of reasoning and computation ever undertaken in astronomy. Why a blurry donut still changed everything. When the Event Horizon Telescope team unveiled the image of M87' in April 2019, many people were surprised at first glance. After years of build-up and decades of speculation, what appeared on the screen was not a crisp, high-resolution photograph like those from the Hubble Space Telescope. It was instead a hazy, glowing ring. For scientists, the blurry ring carried a weight that cannot be overstated. Black holes had long been predicted by Einstein's general theory of relativity, but they had remained theoretical for decades. Evidence for them came indirectly, through the motion of stars, the X-ray emissions of accretion disks, or the strange behavior of galaxies. The dark circle at the center of that ring was not an artist's impression, nor a simulation, but a direct observation. It was as close as humanity could get to looking at the edge of physics itself. The fact that the image was blurry did not diminish its power. In fact, it highlighted the immense difficulty of the task. Even with a telescope the size of Earth, the image was bound to look rough. But the very fact that it looked like anything at all, and that it matched the predictions of relativity, was enough to transform our understanding of what was possible. The donut shape was no accident. It was exactly what theorists had said a black hole's shadow should look like. For decades, simulations of black holes had shown glowing rings caused by matter orbiting the event horizon, distorted by the warping of space-time. Astronomers had confidence in the models, but without a direct image, the predictions remained untested. The EHT's picture of M87 was a confirmation that Einstein's equation still held true in the most extreme environment imaginable. The ring's size, brightness and asymmetry all lined up with expectations for a black hole billions of times more massive than the Sun. Within hours of its release, the glowing ring was everywhere. On the front pages of newspapers, on social media feeds, on television screens around the globe. People who had never studied astronomy before found themselves staring at the face of a black hole, marveling that something so alien could be captured by human ingenuity. Unlike the polished renderings of science fiction, the real picture bore the fingerprints of reality. Blurred edges, uneven brightness, shadows that spoke of turbulent plasma and relativistic motion. The imperfections gave it authenticity. In its roughness, the donut told a story. Nature is not here to present itself neatly to us. We must work to decipher its meaning. The dark center was not literally empty, but represented the region where light paths are bent inward, never to escape. What the EHT revealed was the closest possible outline of the event horizon. Seeing it was like finally glimpsing the silhouette of a creature long known only through footprints and shadows. For the first time, we were not just inferring the presence of a black hole, we were seeing its edge, the very point where space and time collapse into mystery. Before 2019, the average person's mental image of a black hole came from illustrations, films, or simulations. Now there was a real picture to anchor that imagination. Scientists no longer had to rely only on diagrams when explaining accretion disks and event horizons. They could point to the orange ring and say, "There it is." It became an icon, instantly recognizable, like the Hubble Deep Field or the Earthrise photograph from Apollo 8. The fact that it looked so simple made it all the more powerful, a minimalist symbol of the cosmos at its most extreme. For researchers, the image was not the end, but the beginning of a new era. Having seen the shadow once, they knew it could be observed again, in greater detail, with improved arrays of telescopes. Future images might reveal changes in the ring, flickering as plasma swirls and magnetic fields shift. They might even allow astronomers to measure the spin of M87 more precisely, or to test relativity with unprecedented rigor. The blurry donut was not a final product, but a proof of concept, a demonstration that black holes could be directly imaged. The door was now open to discoveries that had seemed impossible only years before. The emotional resonance of the image also came from the knowledge of what it represented about human effort. Behind the orange ring were years of preparation, terabytes of data, and the work of hundreds of scientists around the world. When people looked at the donut, they were not just seeing a black hole. They were seeing the outcome of global cooperation, the triumph of patience, and the culmination of a vision that had once seemed unattainable. Looking at the shadow of a black hole is looking at the edge of knowability itself. No signal can escape, and no telescope will ever peer inside. The donut was therefore both a revelation and a boundary. It gave humanity a glimpse of the abyss, while reminding us that some things will remain forever hidden. The blur was a symbol of the limits of perception, and yet within those limits, we had achieved something extraordinary. Interpreting the brightness asymmetry. The glowing ring was not evenly lit. Instead of a perfect circle of uniform brightness, one side stood out as distinctly brighter. That lopsidedness carried within it a wealth of information about what was happening near the black hole and how matter behaved as it spiraled inward. The brightness asymmetry was not a surprise. Decades of theoretical modelling had predicted that such an effect should appear when observing material moving at relativistic speeds. Gas in the accretion disk doesn't move slowly. It whirls around at incredible velocities. As it does so, the side of the disk moving toward Earth appears brighter, while the side moving away appears dimmer. This is because of a phenomenon known as relativistic beaming. In simple terms, light from particles moving toward us gets boosted, while light from particles moving away gets diminished. The result is a one-sided glow, as if the black hole itself were leaning in our direction. This effect can be compared to the sound of a passing train. As it approaches, the pitch seems higher, and as it moves away, the pitch drops. That change is caused by the Doppler effect, where the motion of the source affects the waves it produces. For light near a black hole, a similar principle applies, but in an even more extreme way. Instead of just a change in pitch, the motion changes brightness. Matter rushing toward Earth emits radiation that is compressed, making it look more intense. Matter rushing away stretches its light, making it dimmer. To astronomers, the brighter side of the ring was therefore a signature of relativity in action. The asymmetry revealed information about the orientation of the system. By studying which side of the ring glowed more brightly, scientists could deduce the direction in which matter was swirling around M87'. This gave hints about the black hole's spin and the tilt of its accretion disk relative to Earth. In M87's case, the brightest part of the ring suggested that the disk is tilted slightly, with one edge coming toward us and the other receding. This aligned well with what astronomers already suspected from observing the galaxy's jet, which shoots outward in a direction consistent with the disk's orientation. This was a crucial test of general relativity. Long before the image was captured, scientists had run countless simulations of what a black hole's shadow should look like. In nearly every case, the result was a dark circle surrounded by a glowing ring with one side brighter than the other. When the EHT data revealed exactly that pattern, it reassured astronomers that their models were on the right track. The asymmetry also deepened our understanding of accretion. Gas near M87' is superheated, turbulent, and magnetically charged. The relativistic brightness boost showed that matter near the event horizon is moving astonishingly fast, circling at nearly the speed of light before finally plunging into darkness. This provided clues about how energy is extracted from the system and how some of it is funneled into the powerful jet. Over time, as matter swirls and magnetic fields shift, the brightest spot on the ring can change. The EHT's first image captured a moment in time, but future observations may reveal how the lopsided glow flickers and evolves. If the brightness shifts in predictable ways, scientists could use it to map the flow of plasma around the black hole, turning the shadow into a kind of cosmic weather report. In fact, follow-up studies comparing data from different years already suggest that the bright side moves, hinting at a dynamic environment far more complex than a steady glow. Because the ring was reconstructed from radio waves using interferometry, there was always the possibility that some details were artifacts of the imaging process. The fact that all approaches revealed the same lopsided brightness gave confidence that what was being seen was real. In science, especially at the edge of the possible, robustness matters. The asymmetry has implications beyond M87 star. If the same effect is observed in other black holes, it could become a standard diagnostic tool, helping astronomers estimate spin, orientation, and accretion properties. By comparing the brightness asymmetry of different black holes, scientists may one day build a catalogue of their spins and orientations, painting a broader picture of how these monsters shape their galaxies. Mass estimates. Refined, weighing the beast with unprecedented precision. Astronomers had long suspected M87 star's enormity by studying the motions of stars and the swirling gas clouds caught in its gravitational grip. But the precise value of its mass had remained an open question. Some estimates placed it at 3 billion times the mass of our Sun. Others suggested closer to 7 billion. This wide range reflected the uncertainties in observational techniques and the difficulty of modelling a system so distant and complex. Pinning down the true figure was important because the mass of the black hole defined the structure of its host galaxy, influenced its jets, and shaped theories about how such a monster could have formed. Traditionally, black hole masses are inferred in two main ways. The first is stellar dynamics, measuring the speeds of stars near the galactic core and using gravity to work backward. If stars are whipping around at extraordinary velocities, only a vast unseen mass could keep them bound. The second approach involves gas dynamics, tracking the rotation of hot plasma disks around the black hole. Both methods are powerful, but each comes with challenges. Stellar motions are chaotic and hard to untangle when viewed from millions of light years away, while gas clouds are buffeted by magnetic fields, turbulence, and radiation. As a result, previous measurements of M87 star's mass did not perfectly agree. The debate had persisted for years, with arguments on both sides. The EHT image offered a new and independent way of weighing the black hole. The size of the shadow is directly linked to the black hole's mass. Light bends around the event horizon in a predictable way, and relativity provides the mathematical relationship between the diameter of the ring and the mass of the central object. Once the image was reconstructed, astronomers could measure the ring's scale and match it to the predictions of Einstein's theory. Unlike the indirect methods of star tracking or gas modelling, this was a more geometric measurement, a simple reading of nature's imprint, like holding a ruler up to space-time itself. The result was strikingly precise. The EHT team announced that M87 star's mass was about 6.5 billion solar masses, with only a modest margin of error. This fell within the broader range of earlier estimates, but leaned toward the higher end, settling years of debate. The convergence between the shadow measurement and some of the better gas dynamic results reassured scientists that their techniques were fundamentally sound, even if less exact. It was not only a refinement, but also a validation. The universe once again had aligned with the predictions of general relativity and with the painstaking work of generations of astronomers who had studied M87. Stars can be placed on scales of brightness, distance, and temperature. Planets can be measured through gravitational tugs or orbital periods. But a black hole has no surface, no features to grab onto, only the gravitational fingerprint it leaves on its surroundings. In M87 star's case, the fingerprint was colossal. 6.5 billion suns worth of matter had collapsed into a region smaller than our solar system. This refined mass also had consequences for understanding the galaxy itself. M87 is a giant elliptical galaxy, one of the largest in the local universe, and it has long been thought that the growth of such galaxies is linked to the growth of their central black holes. The tighter the measurement of M87 stars' mass, the better scientists can calibrate these correlations. It provides an anchor point for scaling relations that connect black hole size with galaxy bulge mass, velocity dispersion, and overall structure. In other words, knowing M87 stars' true mass sharpens our picture of how galaxies and their central engines evolved together over billions of years. M87 stars' size suggests it must have grown rapidly, either through the collapse of extraordinarily large seed black holes in the early universe, or by devouring gas and merging with other black holes at a furious pace. Each scenario has implications for cosmic history, from the formation of the first stars to the assembly of large-scale structures. With the EHT's mass measurement, theorists could constrain their models more tightly, ruling out growth rates or formation paths that did not match the observed data. Astronomers also considered the practical implications for studying M87 stars' jets. With the figure of 6.5 billion solar masses established, simulations of jet dynamics became more accurate. Scientists could feed the number into their models and test whether relativistic magnetohydrodynamic equations could reproduce the observed jet. Once again, the black hole's weight acted as a cornerstone, linking the smaller scales near the event horizon to structures larger than the galaxy itself. The confidence gained from the EHT's measurement also opened the door to comparing M87 star with other black holes. The next major target was Sagittarius A star, the supermassive black hole at the centre of our own Milky Way. While much smaller, only about 4 million solar masses, Sagittarius A star offers a closer laboratory. Together, the two serve as complementary case studies, one massive and distant, the other smaller but near. The mass of M87 star thus became a benchmark, the first confirmed by direct imaging of its shadow, against which others would be judged. 6.5 billion suns is an incomprehensible number, yet the measurement narrowed it down with a percentage-level uncertainty. This was like weighing something the size of Mount Everest from across the ocean and nailing it to within a few kilograms. It demonstrated the extraordinary power of combining human ingenuity with the raw stability of physical laws. For years, astronomers debated, refined, recalculated, and sometimes disagreed about what the numbers should be. Each method brought its own set of assumptions and uncertainties. Yet rather than discarding older work, the EHT's result integrated it, showing that even the indirect approaches had been pointing in roughly the right direction. The shadow was the missing piece of the puzzle, the direct stamp that confirmed decades of inference, the dance of plasma and magnetism around the horizon. When astronomers talk about plasma near a black hole, they mean matter that has been pulled in from the surrounding galaxy. Gas clouds, stellar winds, and even the debris of unlucky stars. Friction between layers of the accretion disk heats the material to temperatures so extreme that it glows across the electromagnetic spectrum, from radio waves to X-rays. The Event Horizon Telescope's polarization measurements gave humanity a rare glimpse into the role of magnetic fields in this extreme setting. Plasma and magnetism form a kind of feedback loop around the horizon. The plasma generates electric currents, which in turn amplify and shape magnetic fields. Those magnetic fields then push back on the plasma, redirecting its flow. In this dynamic dance, energy is redistributed. Some material is funneled inward, slipping past the point of no return. Other particles are flung outward, driven into the jets that M87 hurls into space. One of the great puzzles of black hole physics is why some of this plasma falls inward, while some is expelled outward with such staggering force. Intuitively, one might expect the black hole to swallow everything. But the presence of magnetic fields changes the story. Near the event horizon, these fields can become twisted and wound up by the black hole's spin and the motion of the disk. Like a wound spring, they can release tension explosively, launching particles away at near-light speeds. Observing this dance is extraordinarily difficult. The plasma is billions of light years away, and most of the radiation it produces never reaches us, absorbed by dust or scattered in interstellar space. What the EHT detects are faint radio waves that carry subtle imprints of polarization. Interpreting these requires careful modeling, comparing patterns of polarization in the data to predictions from supercomputer simulations of magnetized accretion flows. These simulations often involve solving equations of general relativistic magnetohydrodynamics, a field that combines Einstein's space-time with Maxwell's electromagnetism and the turbulent motion of fluids. They produce images of disks and jets under different magnetic conditions, which can then be matched against what was seen around M87'. The remarkable agreement between theory and observation suggests that we are, for the first time, beginning to truly read the choreography of plasma and fields near a black hole. To imagine what is happening in human terms, think of a figure skater spinning faster and faster as they pull their arms inward. The skater is the plasma, tightening its orbit as gravity draws it closer to the horizon. Now imagine invisible ropes being tied around the skater's arms and pulled by unseen hands in different directions. Those ropes are the magnetic fields, sometimes guiding the skater into the center, sometimes pulling them sideways, sometimes snapping and sending energy flying outward. The result is a performance both violent and elegant, where order and chaos are inseparable. The presence of strong magnetic fields also affects how efficiently the black hole feeds. If the fields are relatively weak, plasma can flow smoothly inward, feeding the black hole like a steady stream. But if the fields are strong enough, they can actually choke off the inflow, creating the previously described magnetically arrested disk. In such a state, the plasma piles up against the magnetic barrier and the black hole's growth slows. Yet at the same time, the tension in these fields can drive even more powerful jets. This delicate balance between feeding and feedback determines how much energy the black hole releases into its galaxy and beyond. The environment around M87''s horizon is thus a place where the fundamental forces of nature converge in their rawest form. The result is a dynamic interplay, a storm where matter, energy, and space are locked together in perpetual motion. In studying this dance, astronomers are probing the universal mechanisms that operate wherever black holes feed. Two giants, two stories. Why M87' was photographed before our own black hole. It seems almost counterintuitive that the first black hole humanity ever imaged was not the one at the heart of our own Milky Way galaxy. On the surface, Sagittarius A* should have been the easier target. It is only 27,000 light-years from Earth, practically next door on cosmic scales. M87' by comparison is staggeringly distant. Yet when the historic image was revealed in 2019, it was of M87', not Sagittarius A*. The decision wasn't about distance, it was about scale, stability, and the strange quirks of black hole behavior. M87''s sheer size makes it a much easier subject for imaging. The ring of light around a black hole scales directly with mass. In the case of M87', that ring is about 40 billion kilometers across, large enough that even from 55 million light-years away, it subtends an angular size on the sky, comparable to that of Sagittarius A*. Our own black hole is far closer, but it is also tiny by comparison. The shadow of Sagittarius A* is smaller, and though still detectable with the Event Horizon Telescope, it comes with a far greater observational challenge. The difficulty isn't just one of size, it's one of time. Matter near a black hole moves at extraordinary speeds, circling the event horizon in timescales that depend on the black hole's mass. For a giant like M87', material near the horizon can take days or even weeks to complete an orbit. That means its appearance evolves slowly enough that astronomers can combine signals collected over many hours without the image changing drastically. The black hole appears relatively stable, its glow shifting only subtly, while telescopes gather the needed data. Sagittarius A star, by contrast, evolves at breakneck pace. Material whips around its horizon in as little as a few minutes. What the EHT array sees at one moment may look dramatically different a short while later. Imagine trying to take a long exposure photograph of a campfire on a windy day. The result is a blur rather than a sharp image. This is precisely the challenge posed by Sagittarius A star. While M87 star offered something akin to a steady, glowing ember, our local black hole was a flickering flame, its appearance changing faster than the telescopes could capture it in a coherent way. The Earth's rotation, which is crucial for interferometry, compounds this issue. The EHT relies on the planet turning to provide different vantage points, effectively creating a larger synthetic aperture. This process takes hours, but during those hours, Sagittarius A star refuses to sit still. Its turbulent plasma reshapes the emission pattern on timescales far shorter than the imaging process itself. For M87 star, this mismatch between the pace of the black hole and the pace of the Earth's rotation is manageable. For Sagittarius A star, it's a nightmare. The data must be reconstructed from signals that are constantly changing, making the image far harder to stabilize. There is also the matter of interstellar interference. Between us and Sagittarius A star lies the crowded disk of the Milky Way, filled with dust, gas, and scattering effects that distort radio waves. This intervening material acts like a frosted glass window, blurring and scattering the light before it reaches us. M87 star, though vastly more distant, benefits from a clearer line of sight across intergalactic space. Its photons travel relatively unimpeded, giving the EHT a cleaner signal to work with. Paradoxically, the farther black hole had the clearer view. Astronomers also considered the scientific payoff. M87 star was already famous for its spectacular jet. Understanding how that jet connected to the black hole's event horizon was a long-standing puzzle. An image of M87 star promised not only the shadow itself, but also crucial clues about jet formation. By choosing M87 star as the first target, the EHT team positioned themselves to answer multiple questions at once, making the payoff far greater. It's also worth noting that the imaging process was not a one-shot endeavour. The data for M87 star was already extraordinarily difficult to collect. Attempting this feat with Sagittarius A star, with its rapid variability and the distorting effects of the Milky Way in the way, would have been exponentially harder. For a first demonstration of the EHT's power, the team needed a more forgiving subject. M87 star provided that. This choice had echoes of history. When Galileo turned his telescope to the heavens, he did not begin with the faintest stars, but with the bright and obvious targets: Jupiter, the Moon, Venus. Each was chosen because it could yield results that were unmistakable and transformative. The EHT's first foray into direct black hole imaging followed the same logic. Better to start with a giant that could not easily hide its secrets, even from across millions of light years, than to wrestle with a local enigma that would blur and confuse the picture. People often assume that closer means easier, but the universe doesn't play by intuitive rules. Time near a black hole is elastic, and what seems like a short orbital period to matter near Sagittarius A star is enough to scramble our attempts to capture it. M87 star, though vastly farther away, sits in slow motion from our perspective, its titanic mass stretching time itself. In the years after M87 star's image, scientists continued their efforts on Sagittarius A star, developing new algorithms and approaches to tame its variability. They experimented with ways of reconstructing a moving target, akin to stitching together frames from a jittery video rather than relying on a single, long exposure. Eventually, in 2022, they succeeded in revealing Sagittarius A star's shadow too, though it required more sophisticated techniques and a willingness to embrace its restless, flickering character. By then, though, M87 star had already made history, cementing itself as the first black hole ever seen. Galactic context: an elliptical giant versus a quiet spiral core. Elliptical galaxies like M87 are ancient stellar cities. They are packed with billions of old, red stars, most of which have long since burned through their hydrogen fuel. Unlike spirals, which sparkle with the blue light of young, hot stars, ellipticals are dominated by the glow of older populations. Surrounding M87 is a vast reservoir of hot gas, heated to millions of degrees. This gas does not cool quickly, so it does not condense into new stars the way colder gas does in spiral galaxies. Instead, it hangs in place as a diffuse halo, slowly leaking material toward the galaxy's core. This steady supply acts as a cosmic buffet for M87 star, feeding the black hole over long periods and keeping it active. The Milky Way, on the other hand, lives a quieter life. Its spiral arms are nurseries for new stars, and its interstellar medium contains cold clouds of hydrogen gas. But near the center, the conditions are not as favorable for constant feeding. Sagittarius A star has very little material immediately around it, compared to M87 star. Stars pass by, stellar winds contribute gas, and sometimes clouds drift near, but the feeding is irregular and sparse. This makes Sagittarius A star faint in nearly every wavelength, so much so that it remained a hidden giant until radio observations revealed its presence. In contrast, M87 star's activity shines across the spectrum, making it a much louder presence in the cosmos. These differences extend beyond feeding habits to the way the black holes influence their host galaxies. Sagittarius A star does not have a prominent jet, and though it has flared in the past, today it is subdued. The Milky Way continues forming stars at a steady rate, largely unaffected by its quiet central black hole. The scale of the galaxies also matters. M87 is a true giant, far larger than the Milky Way, containing more stars and more mass overall. Its central black hole is scaled up accordingly. Sagittarius A star is enormous by human standards, but it is tiny compared to M87 star. The difference in scale creates differences in the pace of activity, the strength of gravitational pull, and the amount of energy released into the environment. When astronomers compare the two, they gain a window into the diversity of galactic cores and how black holes adapt to their cosmic surroundings. Another striking difference lies in their cosmic neighborhoods. The Milky Way inhabits a quieter corner of the cosmos, part of a smaller group of galaxies with relatively little drama. Without abundant interactions, Sagittarius A star has fewer opportunities to feast. These contrasts teach astronomers that black holes are not just shaped by their own physics, but by the larger galactic ecosystem they inhabit. The blazing activity of M87 star is not just a product of its spin or its magnetic fields, but of the galaxy's nature as an ancient gas-rich elliptical in a dense cluster. Sagittarius A star's quietness, by contrast, reflects the Milky Way's spiral structure, its less violent neighborhood, and its irregular feeding patterns. Together, the two systems highlight how the destiny of a black hole is deeply tied to the story of its galaxy. Shared lessons and diverging questions. When the Event Horizon Telescope revealed the shadow of M87 star, it showed that space-time bends light just as relativity predicts. When the image of Sagittarius A star followed, it showed the same result, despite the black hole being thousands of times smaller and living in a very different environment. This consistency is crucial because it suggests that our theories are not fragile. They hold even in places where gravity crushes matter into unimaginable densities. The matching of theory and observation is one of the clearest signals that Einstein's work remains the backbone of modern astrophysics. But even with this confirmation, the contrasts spark fresh questions. Why does M87 star have such a powerful, extended jet, while Sagittarius A star does not? Both have magnetic fields. Both have plasma. Yet only one produces a structure so immense it stretches thousands of light years. This difference pushes scientists to think beyond the idea that all supermassive black holes behave alike. Perhaps it comes down to feeding. M87 star has an abundant supply of hot gas constantly streaming toward it, while Sagittarius A star has very little to consume. The difference in diet could be the deciding factor in whether a black hole becomes an active galactic nucleus or sits dormant. But feeding alone may not explain everything. Spin could matter too. If Sagittarius A star spins slowly, that could explain its quiet state. Yet measuring spin directly remains challenging, leaving this as an open mystery. And then there is the broader question: how typical are these two examples? Together, they bracket two very different regimes, but there are countless other supermassive black holes across the universe. Some blaze as quasars, outshining their galaxies. Others sit in near silence, detectable only through the motions of nearby stars. By comparing M87 star and Sagittarius A star, astronomers hope to place these giants within a larger spectrum, mapping out the diversity of behaviours that supermassive black holes display. If black holes are governed by the same physics, why do they express it in such varied ways? Is there a clear dividing line between active and dormant black holes, or is it more like a sliding scale? What role does the history of a galaxy play, its collisions, its gas supply, its structure, in determining what its central black hole becomes? These are not trivial questions. They reach to the heart of how galaxies, and by extension the universe, evolve over billions of years. What makes the comparison of M87 star and Sagittarius A star so powerful is that they give us real, visible data. For decades, black holes were studied indirectly. Now, with images, we can compare their shapes, their brightness, their stability. It is like finally seeing two animals in the wild that had only ever been described from footprints and distant calls. And just as biologists learn by comparing species, astronomers learn by comparing black holes. In many ways, the shared lessons offer a kind of cosmic reassurance, but the diverging questions keep the field alive with mystery. Why does one roar while the other whispers? Why do some galaxies revolve around raging hearts while others around sleeping ones? Each new observation both clarifies and complicates our picture of the cosmos. The deeper scientists look, the clearer it becomes that there is no single story of what a supermassive black hole is. There are instead many stories, each tied to the galaxy it inhabits, each shaped by scale, environment, and history. M87 star and Sagittarius. A star are two chapters in this larger narrative, teaching us that the universe operates under common rules. But those rules can unfold in dramatically different ways. In that tension between sameness and difference lies the true power of comparison. Limits of knowledge, what the first image couldn't tell us. When the image of M87 star was released, it was hailed as a historic achievement, and rightly so. Yet behind the celebration, scientists were quick to acknowledge its limitations. The technology was pushed to its limits, and while it opened a new window, that window remained foggy. The very fact that it looked like a donut rather than a crisp structure spoke volumes about what we could not yet discern. One of the most obvious limitations concerned the spin of the black hole. Spin is not a minor detail. It's a fundamental property as important as mass, shaping everything from the way space-time swirls to the mechanism by which jets are launched. The direction and speed of spin could tell us whether M87' has been steadily feeding in the same orientation for billions of years, or if violent galactic mergers twisted and tilted it over time. But the EHT's first image could not provide a definitive measurement. The asymmetry of the bright ring gave hints, suggesting that matter may be orbiting in a particular direction, yet it stopped short of revealing precise numbers. Determining spin requires either sharper resolution or other complementary observations, such as tracking how the jet wobbles over long timescales. Another unresolved mystery was the small-scale structure of the accretion disk itself. In theory, the accretion disk is a finely detailed environment with hotspots of plasma forming, breaking apart and reforming in turbulent motion. Magnetohydrodynamic simulations suggest that the disk may flicker and twist with astonishing complexity, producing patterns of brightness that evolve on timescales of hours or even minutes. But the image we saw in 2019 was not capable of capturing such rapid or fine-grained variability. Instead, the algorithm stitched together data collected over days, effectively smoothing out fluctuations into a single static frame. If the accretion disk is alive with activity, we saw only the average glow, not the intricate dance that makes it so fascinating. The inner jet remained shrouded in mystery as well. Astronomers had long theorized that the jet emerges from the very edge of the black hole, tied to its spin and magnetic field lines. The EHT image hinted at this connection, but it did not resolve the actual launch point in detail. What precise mechanism accelerates matter to nearly light speed? Does the jet originate from the innermost regions of the accretion disk or directly from the black hole's spinning ergosphere? The blurry outline left both possibilities on the table. Even with the jet observed for decades at larger scales, the crucial birthplace where theory meets reality was still cloaked. The shadow itself left questions about deviations. General relativity predicts a nearly perfect circular silhouette, slightly distorted only by spin and perspective. The observed shadow matched these predictions well, but the precision of the match was limited. Could small deviations exist, ones that might hint at new physics beyond Einstein? With current data, scientists could not say. The uncertainty bars were too wide, the resolution too coarse. For all we know, subtle cracks in our understanding could be lurking, invisible, until sharper eyes reveal them. Even the process of making the image raised challenges. The data had to be carefully cleaned, stitched and reconstructed using algorithms designed to avoid injecting bias. Similarly, the EHT's global array was powerful, but it still had gaps in coverage, like missing puzzle pieces. The image we saw was the best reconstruction possible from an incomplete dataset. That means it was not a direct photograph, but an interpretation, one supported by careful cross-checking, yet still bound by limitations. Time also posed a problem. A black hole's environment is not static. Plasma whirls, magnetic fields shift, and structures form and dissolve in rapid succession. Yet the EHT did not capture a real-time video. It captured snapshots spread out over multiple nights. When these were combined, fleeting details blurred away, leaving only the stable features. This was enough to reveal the shadow, but it erased the possibility of watching the black hole's immediate surroundings evolve moment by moment. To see such dynamics, astronomers would need instruments capable of sustained, continuous observation with even greater precision. The wavelength used for observation, millimeter radio waves, offered one kind of information, but it could not tell the full story. Other wavelengths, like X-rays or gamma rays, probe hotter, more energetic regions closer to the event horizon. Coordinated observations across the electromagnetic spectrum are crucial to piece together the full puzzle, yet the first image alone could not accomplish this. It was one slice of a much larger, multi-layered phenomenon. Without the rest, key details about the energy flow and particle acceleration remained hidden. Breakthroughs rarely provide final answers. Instead, they clear the fog just enough to reveal new questions. M87's portrait reminds us that the universe keeps its deepest secrets close. The spin, the exact jet mechanism, the turbulence of plasma, the potential for deviations from relativity, all these remain just beyond reach, waiting for the next leap in technology. Polarized light, peering into magnetic structures at the event horizon. In 2021, 2 years after the first image, the EHT collaboration released the first polarized light view of a black hole's shadow. To most people, the new picture looks similar to the original ring, only with faint lines drawn across it, like tiny arrows. But to astronomers, those lines represented the fingerprints of magnetic fields at the very edge of M87'. Ordinary light waves vibrate in all directions, like ripples moving randomly across the surface of a pond. But when light interacts with magnetic fields or bounces off aligned particles, it can become polarized, meaning its waves vibrate mostly in one direction. In the case of M87', the polarized light observations were nothing short of a revelation. The faint polarization lines etched across the glowing ring revealed that strong magnetic fields threaded the plasma swirling around the event horizon. Instead of chaos without order, there was structure. Magnetic lines coiled and stretched, channeling energy and matter in specific directions. Measuring polarization is far more difficult than simply detecting light. It requires collecting faint signals from across the globe with exquisite precision, then teasing out tiny differences in the direction of light waves from an ocean of noise. The resulting image showed that about 15% of the light around M87' was polarized. This may sound small, but in astrophysical terms, it is remarkably high. It means that the plasma near the black hole is strongly influenced by magnetic fields, rather than being a purely random swirl of gas. The polarization vectors lined up in patterns that curved around the ring, suggesting fields twisted by the black hole's spin and the motion of the accretion disk. In some regions, the polarization lines pointed outward, hinting at fields channeling plasma away from the horizon, perhaps the very seeds of the jet observed shooting from M87's core. To make sense of these patterns, scientists compared the data to simulations of how magnetic fields and plasma interact near a black hole. The models that best matched the EHT observations were those in which magnetic fields are dynamically dominant. In these scenarios, the fields are strong enough to resist being completely dragged into the black hole, instead shaping the flow of matter and extracting energy from its rotation. The polarization map of M87' was a direct glimpse of magnetic fields doing the heavy lifting at the event horizon. The discovery also suggested that magnetic dominance might be a general property of actively feeding supermassive black holes, wherever they are found. If true, it would mean that jets and energetic outflows are not exotic accidents, but natural consequences of black holes interacting with their environments. This helps explain why jets are seen across the universe, from galaxies near and far, always tied to the presence of accreting black holes. The polarized light of M87' thus provided not just local insight, but a universal principle. Yet as with all breakthroughs, the findings raised as many questions as they answered. For one, the precise geometry of the magnetic fields remains uncertain. The polarization patterns show their general alignment, but the three-dimensional structure is far more complex. Do the fields form closed loops around the black hole, or do they thread outward into space, anchoring the jet? Are they stable over time, or do they tangle and reconnect? These questions can only be answered with sharper, time-resolved observations. Another mystery lies in the efficiency of the process. If magnetic fields extract energy from the black hole's spin, how much can they take before the black hole slows down? The raw polarization data was messy and incomplete. To turn it into a coherent map, scientists relied on algorithms that reconstructed the most likely arrangement of fields consistent with both observation and physics. This interplay between data and theory is delicate. Too much reliance on models could introduce bias, but without models, the data would remain incomprehensible. The success of the project demonstrated a balance: how careful, transparent use of simulations can bring hidden structures into view without replacing reality with expectation. Looking ahead, polarization studies promise to deepen our understanding of black holes. Future upgrades to the EHT will improve both resolution and sensitivity. This means finer polarization maps, sharper traces of magnetic fields, and perhaps even the ability to watch them evolve in real time. If scientists can observe how magnetic fields twist, snap, and reform around the event horizon, they will have a front row seat to the engines that drive some of the brightest phenomena in the universe. Where the first black hole image revealed the shadow of gravity, the polarized image revealed the threads of magnetism. Together, they tell a story of balance between chaos and order, collapse and outflow. Sharper eyes, the promise of primo and machine learning reconstructions. The image of M87' was a triumph, but also a compromise. It was the sharpest possible picture that could be produced using the EHT's vast array of instruments and the immense processing effort that followed. Yet it was still limited by the raw data available. For most people, that image was already revolutionary. For scientists, it was only the beginning. They knew there were hidden structures, subtle brightness variations, and sharper boundaries buried in the data, if only they could find a way to bring them out. That opportunity arrived in 2023 with the introduction of Primo, a machine learning technique designed specifically to reconstruct sharper images from sparse and noisy data. Primo stands for Principal Component Interferometric Modeling. It represents an entirely new way of approaching the challenge of imaging something as elusive as a black hole. Instead of simply taking the data as it is and stitching it together with traditional algorithms, Primo uses the power of artificial intelligence to recognize patterns and fill in missing information in a way that is consistent with physics. In essence, it gives astronomers a set of sharper eyes, allowing them to glimpse details they could not otherwise resolve. The core idea behind Primo is training. The method begins by generating a library of simulated black hole images built from computer models of how matter and light behave around an event horizon. These simulations account for the effects of gravity, relativity, plasma physics, and magnetism, creating thousands of possible versions of what a black hole might look like under different conditions. Primo then learns from this library, teaching itself the statistical patterns of black hole images, what rings look like, how brightness changes, how asymmetries form. Once trained, it can take the real, incomplete data from the Event Horizon Telescope and reconstruct a more detailed picture by leaning on its learned knowledge of black hole physics. This is not the same as simply making up a sharper picture. The machine is constrained by both the data it is given and the physics encoded in the simulations. Every detail it fills in has to be consistent with both. That balance is what makes Primo powerful. It bridges the gap between observation and theory, between raw measurement and physical expectation. Instead of guessing, it refines. It brings out what is already implied in the data, but hidden beneath its limits. When the Primo reconstructions of M87' were revealed in 2023, the difference was striking. The black hole's shadow looked more defined, the ring sharper, and the brightness asymmetry clearer than before. What had once seemed like a vague haze now looked like a structured, glowing ring with fine features. The image retained the same overall size and shape, confirming the validity of the original, but it offered a level of detail that felt like stepping closer to the event horizon itself. For scientists, this was not just an aesthetic improvement. It was a tool for deeper measurement, a way to refine estimates of the black hole's properties and test relativity with greater precision. The PRIMO results showed that machine learning is not just a tool for processing data faster. By combining the raw power of observation with the pattern recognition abilities of artificial intelligence, astronomers could push beyond the apparent limits of their instruments. In many ways, it is the continuation of a trend that has always defined astronomy. For centuries, scientists have relied on instruments not just to extend vision, but also to interpret it. Glass lenses, photographic plates, CCD sensors, computer algorithms. Each step brought new clarity. Now, neural networks join that lineage, acting not as replacements for telescopes, but as partners to them. Yet the use of machine learning in something as delicate as black hole imaging is not without controversy. Some scientists worry that relying too much on simulations could bias the results. After all, PRIMO is trained on models of black holes that are built from our current understanding of physics. If reality turns out to be stranger than expected, could the algorithm unintentionally smooth over those differences? Could it hallucinate features that align with theory, but not with nature? These concerns highlight the importance of caution. The PRIMO reconstructions are not meant to be treated as the final word, but as another layer of interpretation, to be tested and cross-checked against other methods. The EHT cannot record every frequency of light, nor can it place radio dishes in every location on Earth. There will always be gaps, blind spots, and noise. Machine learning offers a way to bridge those gaps responsibly, pulling out the maximum amount of information without violating the rules of physics. In practice, this means that the black hole's spin, orientation, and magnetic environment can be studied with greater precision. It also means that subtle changes over time, flickers in brightness, shifts in asymmetry, can be tracked more clearly. The success of PRIMO with M87' sets the stage for similar applications with Sagittarius A*. Sagittarius A* is even harder to image, and machine learning may be the key to untangling this mess, separating the rapid variability from the underlying structure. If PRIMO or its successors can sharpen the view of Sagittarius A*, we may get a stable, highly detailed image of our own black hole. Beyond black holes, the techniques pioneered by PRIMO could spread to other areas of astronomy. Interferometry is used not only for black holes, but also for studying distant galaxies, exoplanets, and star formation. Anytime data is sparse or noisy, machine learning has the potential to improve clarity. This points toward a future where observation and computation are inseparable, where telescopes collect signals and algorithms immediately begin reconstructing them into richer forms. PRIMO embodies a shift in how humanity approaches the unseeable. For centuries, we accepted that some things would always remain hidden. But with tools like this, the line between visible and invisible begins to blur. For the first time, we are not just passively observing the universe, we are actively collaborating with it, refining our perception to match the scale of the mysteries we seek to unravel. Future telescopes in space, taking EHT off-planet, very long baseline interferometry relies on spacing antennas as far apart as possible to sharpen the resulting vision. Yet no matter how far the dishes are spread across continents, Earth itself is the limiting factor. The maximum distance between any two stations can never be larger than the planet's diameter, about 12,742 kilometers. It is an impressive baseline, but when it comes to black holes that sit tens of millions of light years away, the Earth is still far too small a lens. The idea now emerging is simple in principle, but extraordinary in scope: to take the Event Horizon Telescope into space. A space-based extension of the EHT would fundamentally change what is possible. Instead of being restricted by the boundaries of Earth, astronomers could place telescopes in orbit, stretching the effective baseline by orders of magnitude. Imagine antennas circling the planet in low Earth orbit, others drifting at lunar distance, and perhaps some even stationed at Lagrange points far from Earth. Each additional separation adds resolution, like swapping a magnifying glass for a microscope. The ring around M87', which now looks like a fuzzy band, could be sharpened until finer substructures become visible. Instead of simply confirming the existence of the shadow, scientists could begin probing turbulence, hotspots, and dynamic ripples at the edge of the abyss. Proposals for space-based interferometry have been floating in scientific literature for decades. Early ideas, such as the Japanese-led VSOP mission in the 1990s, already placed a radio telescope in orbit to link with ground facilities, proving that space VLBBI was technically feasible. The successor mission, Radio Astron, extended this approach from 2011 to 2019, joining Earth telescopes with a satellite dish in highly elliptical orbit. The results demonstrated that space-based baselines could provide the sharpest images in the history of radio astronomy, surpassing Earth-only networks. If such technology could be adapted to the frequencies used by the EHT, the leap forward in resolution would be staggering. One of the greatest advantages of putting telescopes into space is the escape from atmospheric interference. Earth's atmosphere, while life-giving, is a nuisance for astronomers. It distorts signals, absorbs certain wavelengths, and introduces noise that must be filtered out with complex calibration. A dish orbiting high above this turbulent blanket would enjoy a clear view of the cosmos. No weather delays, no tropospheric fluctuations, no interruptions by rain or snow. Every second of data gathered would be cleaner, requiring less correction and ultimately yielding sharper reconstructions of the black hole's image. In practical terms, a space-based EHT might begin modestly. A single antenna in orbit could double or triple the effective resolution of the network. The addition of more satellites would continue multiplying the gains, especially if they were carefully placed in orbits that maximize separation over time. A constellation of such instruments could, in principle, extend the baseline to hundreds of thousands of kilometers. At that scale, even distant supermassive black holes like M87' would reveal structures invisible to us now. And for the much closer Sagittarius A star, in the center of our own galaxy, we could capture dynamics unfolding in real time with unprecedented clarity. This approach could also address one of the major challenges that the current EHT faces: coverage. To reconstruct an image, the interferometer needs data from many different points in the virtual lens. But because the Earth rotates and stations are fixed, there are gaps, blind spots that limit the completeness of the final image. Adding satellites in orbit fills in those gaps, providing new baselines and richer data sets. A sharper EHT could also probe the jets streaming from galaxies like M87. It could examine accretion flows in exquisite detail, distinguishing between competing models of how matter spirals inward. Even the physics of space-time could be tested more rigorously, as subtle deviations from general relativity might be revealed in finer measurements. The potential scientific payoff is vast, cutting across astrophysics, plasma physics, and fundamental physics. Of course, the road to such a network is not simple. Launching large radio dishes into orbit presents significant engineering challenges. Spacecraft must survive extreme conditions while maintaining the precision required for interferometry, where signals must be synchronized to fractions of a nanosecond. The logistics of data transfer are also daunting. Transmitting petabytes from orbiting satellites poses a formidable problem, one that will require new solutions in communications and data handling. Yet the momentum is building. In recent years, agencies and research teams have begun sketching out designs for missions that could extend the EHT into space. Some concepts involve compact, foldable antennas that could be deployed aboard relatively small satellites, making the cost more manageable. Others imagine international collaborations, with multiple space agencies pooling resources to construct a distributed array beyond Earth. Private space companies, with their rapidly growing launch capabilities, may also play a role, reducing the barrier to placing scientific payloads in orbit. The first image of M87' captured the public imagination because it represented a collective achievement, a planetary collaboration stretching across continents. A space-based extension would be even more audacious, a truly cosmic observatory, using Earth as just one node in a much larger network. It would embody humanity's desire to see the unseen, to sharpen our vision beyond natural limits. The blurry donut might one day be replaced by a portrait so clear it reveals the living, shifting edge of a black hole. Once, telescopes were solitary instruments gazing at the sky. Then they became global networks, linking across the Earth. The next step is to push those networks into orbit, weaving Earth and space into a single eye. For black holes, this may be the only way to truly peel back the veil and witness their hidden engines at work. If the EHT gave us the shadow, then its spaceborne successor could give us the face of the abyss. The dream of black hole movies, time-lapse imaging of M87'. A movie requires multiple frames captured over time, stitched together to reveal change. For a black hole, this means observing the same object repeatedly and with enough consistency to see patterns emerge. Unlike distant galaxies that remain relatively static on human timescales, the environment near a black hole is restless, and capturing this dance requires patience, precision, and the ability to separate real motion from the noise of observation. In this pursuit, M87' has one crucial advantage: size. For astronomers, this means they can collect data with the EHT across multiple nights, piecing together a coherent sequence without the risk that everything has changed in the blink of an eye. The slower pace of M87' makes it the perfect stage for time-lapse astrophysics. Already, the first steps towards such a movie have been taken. When the 2019 image of M87' was unveiled, it was not just the product of a single night's observation. The EHT had collected data over 4 separate days in April 2017. Each day produced its own version of the black hole's ring. Subtle differences appeared: shifts in brightness, slight changes in the glow around the shadow. In fact, the EHT collaboration later released a sequence showing these daily variations, an early teaser of what a true black hole movie could one day look like. Even in this rough form, the effect was profound. The shadow of M87' seemed to shimmer, its luminous edge flickering, reminding us that black holes are not fixed monuments. To turn such glimpses into real movies, however, demands upgrades to the observing network. The EHT is currently limited by the number of stations and the quality of its coverage. A movie would require a steady stream of frames with fewer gaps, sharper resolution, and better timing. Each additional telescope added to the network improves this, filling in missing pieces of the puzzle. Plans to expand the EHT with new dishes in Africa, Europe, and space all feed into this ambition. The sharper the vision and the broader the coverage, the closer we get to watching a black hole in motion. The scientific payoff would be enormous. Still images already confirmed Einstein's predictions. Moving pictures could test theories in far greater detail. By watching how bright spots in the plasma orbit, scientists could measure the spin of the black hole more precisely. They could track the interaction between inflowing matter and outflowing jets, a mystery that remains unsolved. They might even catch sudden bursts or flares, revealing how energy is unleashed in short, violent events. Every frame would carry new physics, and every shift in the glowing ring would be a clue to the black hole's hidden workings. The dream of movies also carries something more intangible, an emotional impact. A still image stirs curiosity, but a moving image creates connection. To watch the edge of a black hole change, frame by frame, would make it feel less like an abstract concept and more like a living phenomenon. Just as early photographs of Earth from space transformed how we see our planet, a movie of M87’ could reshape how humanity imagines black holes. There are, of course, challenges. Even with M87's slower timescales, the changes are subtle. The plasma ring may brighten on one side, dim on another, or warp slightly under magnetic pressure, but the central shadow remains constant. Distinguishing meaningful variations from observational noise requires enormous care. Machine learning will likely play a central role in reconstructing moving sequences. Algorithms, such as Primo, could be adapted to smooth transitions between frames and highlight real structures without inventing false ones. The fusion of observation and computation will be essential. The first true black hole movies will not resemble the cinematic visions we are used to in science fiction. They will not show crisp arcs of fire swirling dramatically around a glowing abyss. Instead, they will likely be ghostly animations of shifting light, faint rings fading and reappearing, hotspots orbiting like embers in a storm. But to astronomers, these subtle variations are far more valuable than spectacle. They encode the physics of plasma under extreme gravity, offering direct evidence of processes we have only modelled in supercomputers. Even if the public sees only a flickering ring, scientists will see equations come alive. If we can master the art of time-lapse imaging, we might eventually attempt movies of Sagittarius A star. Though its smaller size makes the task too difficult for the current EHT, future telescopes, especially those in space, could freeze those rapid motions with enough precision. Watching our own galaxy's black hole flicker in near real time would be like peering into a local storm, far more chaotic than the stately whirl around M87’. Together, the two movies would provide contrasting portraits of how black holes feed and flare, a comparative cinema of cosmic extremes. As with all pioneering visions in astronomy, patience is key. The first movies may take years to assemble, with each frame built from nights of data collected across continents. They may appear coarse at first, just as the first still images did, but with every upgrade, with every added telescope, and with every refinement in reconstruction, the moving picture will sharpen. Step by step, frame by frame, the dream will come closer to reality. We are used to thinking of black holes as eternal, unchanging voids, their lifetime stretching across the ages of the universe. To compress their motions into movies that we can watch is to bring them into our scale of time, to see them not as distant abstractions, but as phenomena unfolding before us. What comes after? The next era of black hole astronomy. When the first images of M87 were unveiled, it was easy to feel as though astronomy had reached a peak. Yet in science, milestones are never destinations, they are doors. The blurry orange ring that captivated the world was not the final chapter in black hole astronomy, but the prologue. It signaled the beginning of an era in which black holes are no longer just theoretical constructs or mathematical predictions, but observable objects, testable under conditions that push physics to its breaking point. What comes next promises to be even more profound. The shadow of M87 was only a fraction of the story. Around that shadow lies a turbulent world of plasma, magnetic fields, and violent energy transfers. An astrophysical lab more extreme than anything we could ever create on Earth. To understand black holes fully, we need to go beyond shadows and still images, diving into their inner workings in greater detail than ever before. One of the most tantalizing frontiers is the study of black hole mergers. So far, these cosmic collisions have been detected only through gravitational waves, ripples in space-time captured by detectors like LIGO and Virgo. These signals tell us when two black holes spiral together and merge into one, but they cannot show us what such an event looks like. Future versions of the EHT, especially if expanded into space, could one day resolve the light emitted when matter swirls during these cataclysmic unions. The prospect of pairing gravitational wave detections with direct visualizations is electrifying. Two completely different windows on the same event merging to give us a full picture of some of the most violent processes in the cosmos. Accretion flows, the lifeblood of black holes, are another target for the coming era. In the first image of M87's, the accretion disk appeared only as a faint ring of light. But this ring hides complex behavior, and with sharper instruments, astronomers hope to map these flows with precision. Doing so would not only illuminate the feeding habits of black holes, but also explain how they regulate the galaxies around them. To decode this influence, we must track their meals in detail. Beyond astrophysics, black holes remain our best probes of fundamental physics. Relativity describes the large-scale structure of space-time, while quantum mechanics rules the small, and the two frameworks remain deeply incompatible. Black holes sit at the intersection, their singularities representing a breakdown of our current understanding. By observing them with increasing precision, we may find cracks in Einstein's model. These would not disprove relativity so much as point toward the next theory, the long-sought union of gravity and quantum mechanics. The possibility of new physics is what drives many of the boldest ideas in black hole astronomy. Some researchers wonder if exotic objects, like wormholes or boson stars, could mimic black hole shadows, but leave subtle differences in their signatures. Detecting such anomalies would revolutionize not just astronomy, but our entire conception of reality. While M87' and Sagittarius A* show strong agreement with Einstein's predictions, future telescopes may uncover subtleties invisible today. The edge of a black hole is the sharpest testbed we have for the laws of nature, and the deeper we peer, the more those laws may reveal their hidden layers. Achieving these breakthroughs requires instruments far beyond today's limits. Expanding the EHT into space is one path forward. Placing radio telescopes in orbit or even on the Moon would create baselines larger than Earth itself, sharpening resolution by orders of magnitude. With such a network, astronomers could zoom into features just a few light hours across, perhaps watching bright plasma knots circle the event horizon in real time. Black hole movies would not be limited to crude time lapses, but could show intricate dynamics with clarity. Space-based interferometry, though still in its early planning stages, has the potential to transform the field as dramatically as the Hubble Space Telescope transformed optical astronomy. Algorithms like PRIMO have already demonstrated how vast libraries of simulations can guide reconstructions of incomplete data. In the next era, these computational methods will grow even more powerful, able to extract finer details and separate real structures from noise. This marriage of human ingenuity, computer intelligence, and cosmic data represents a new kind of science. The images of tomorrow will be produced by a synergy of instruments and algorithms, working together to reveal what would otherwise remain hidden. Our own supermassive black hole remains a central focus. With new instruments, we may finally measure its spin, observe its bursts with greater clarity, and connect those bursts to changes in the surrounding gas. On the larger scales, future black hole astronomy may even help answer questions about the universe as a whole. If black holes grow by swallowing matter and merging with one another, then their populations encode the history of galaxy formation. By tracing that history, we could learn not only how galaxies like the Milky Way formed, but also how the cosmic web itself evolved. Black holes, once thought of as dead ends, now appear as keystones in the structure of the cosmos. Their study will shape our understanding of cosmic history as surely as it will test the laws of physics. The next era will unfold step by step, but each leap has the potential to rewrite our relationship with the universe. In the near future, we may watch plasma swirl around the event horizon, trace jets to their roots, or glimpse the fireworks of black hole collisions. In the more distant future, we may discover phenomena so unexpected that they force us to rethink the very nature of space and time. For now, the shadow of M87 star remains our guide. It was the first glimpse of a place where light ends and gravity reigns supreme. But it will not be the last. That simple, glowing ring opened the door to a future where black holes are no longer mysteries glimpsed from afar, but worlds we can watch, measure, and learn from. The shadow was the beginning. What comes after may be the deepest journey science has ever taken. Which aspect of this future are you most excited for? Leave a comment down below, and if you enjoyed this voyage, consider leaving a like and subscribing to the channel. Thanks for watching.